Um, first item on the agenda is introductions. So let's start with those. Hi, everyone. My name's Gareth Funning. I'm a professor of seismology at the University of California, Riverside. I didn't choose my job title. Someone decided I was a professor of seismology. I do study earthquakes, and I mostly study them with InSAR. I'm the lead instructor of this course, along with Franz Meyer, who is also on the call.
Yes, so my name is Franz Meyer. I'm at the University of Alaska Fairbanks, where, by the way, fall has started. I drove to work today and there were lots of trees that had yellow leaves. So we are starting fall really early this year. I've been in the SAR business since around 2000 when I started my PhD. My PhD work was on sort of time series glacial remote sensing and methods development to facilitate that. Then I worked for a few years at the German Aerospace Center on the TerraSAR mission, and then came to Alaska, where I'm also the chief scientist of the Alaska Satellite Facility. I'm on the science team of NISAR. We're super excited to see that mission take off. And maybe my first interferograms that I created were over an archipelago called Franz Josef Land, which belongs to Russia. And I made my PhD maybe on 25 interferograms. You won't get quite as lucky because Sentinel is shelling you with data and NISAR will shell you with data. So you will need lots more data these days. And I hand it to Eric.
Yes, my name is Eric Fielding. I'm a geophysicist at the Jet Propulsion Laboratory. I've been doing INSAR since about 1995. And I'm on the NISAR project science team. That's what this model is in the background here. NISAR is finally in space, and they've deployed the reflector that you see there, and we're hoping to start getting data in the near future. I primarily work on earthquakes and landslides and a few other applications of INSAR.
Who else is on here? Anne is on here.
Hi, everyone. I'm Ann Chen. I'm an associate professor at University of Texas at Austin in aerospace engineering, but INSAR is an interdisciplinary field. My training is, I got my PhD in geophysics in 2014. So the field of INSAR has been evolving rapidly. So back then, when I was a PhD student, I got the brand new TerraSAR X data, and I was bragging to people, I have 300 interferograms, a super large size of a stack of data. And now we routinely process thousands of interferograms. So I really look forward to share what I know and with you this week. And so hopefully we're going to have a lot of fun.
Great. How about Scott next?
Hello, I'm Scott. So I was actually Anne's student at the University of Texas. So I learned about INSAR from Anne, and I graduated in 2022. I did an internship at JPL, and then I joined in 2022 in the radar science, the SAR algorithms group. And most of my work at JPL has been on the Opera project. So that's a pretty large project giving a bunch of a variety of remote sensing products that are trying to be easy to use and analysis ready for mostly federal users, but they also have science applications. So I've been working, and right now I'm the lead on the surface displacement product. So we're making a big North American surface displacement product that you can download and use. And we'll talk about that later in the week, as well as the libraries that we have that are open source that we are running in production to process this data.
Sarah turned her camera on, so we'll go to her next.
Hello, I'm Sarah Mirzai. I started working with SAR data when I was a master's student. I started with polarimetric data, and then I continued with INSAR throughout my PhD, and now I'm working with the Opera displacement team, with Scott mainly, in JPL.
Becca is here.
Yeah. Hi, my name is Becca. I'm currently a postdoc at Penn State. I got my PhD last June. I work primarily looking at volcanic deformation with InSAR and also doing a bit of coastal subsidence now, getting into that. Yeah, my first interferograms were over two Nicaraguan volcanoes, Tilica and Masaya, and I'll just be around helping out during office hours and with any questions you guys might have throughout the week.
Thanks. I think that's it for
Zach,
instructors right now. Zach,
Are you still on?
I think he was the sacrificial person who went off into the other Zoom room. He will come back at some point. Well, great. Welcome, everybody. That's a subset of our instructor pool. We have a few others who'll drop in from time to time. For some of whom, this is not their primary time zone, and so we'll give them a bit of a break. Especially Yunjun, who will be here on Friday. This is like very, very early in the morning for him, I think. But we can show you what we have in store for you today, and that's the next thing on the agenda. So I'll share my screen just now, just briefly, and I'll bring up what is the syllabus document for the course, which is linked to from the Moodle. So if you have access to our Moodle page, the syllabus page here has a version of the syllabus in a document, but it also has this link, and this link, if you click it, will take you to this syllabus document. So in here, you can scroll down. There's a bunch of links and things. If you were at any of the kickoff meetings, I went through this in laborious detail, so I don't have to do that now. But basically, what we've got is the agenda for today in here, day one, right? So we've just had our welcome session. This is the agenda review. I'm about to show you what we're going to talk about today, and in a minute, Franz will take us through how you log into the OpenScienceLab for those who did not see that yet. And at around 10:30, which is not very far away in time, I will give a brief lecture about an introduction to modeling with geophysical data, a very, very brief introduction to InSAR. And that will be followed by Franz leading an exercise in actual geophysical modeling, where we take some data from a volcano and try and model it. After a short break in the afternoon, California time, at noon, and we'll lead a session on InSAR Theory. And then the final act of the day will be this module on interpretation of data that I will be leading. So that's what you have in store for you today. Please note that there are office hours that start at 5 p.m. Pacific time, so 3 hours after the end of the main session. And there will be another set of office hours tomorrow morning at 7 a.m. Pacific time. So whatever that resolves to in your local time zone. The intent is to have two sessions at sufficiently different times that they should work for one. One of them should work for everybody who's signed up for the course. So that's the agenda for today. Franz, do you want to take over and do your OSL thing?
Sure. Let me. Can you guys hear me? Yeah, I think so. Share my screen. So you should see my entire desktop right now. Is that correct? So if you go to the syllabus document, in several places in the document, and also on the Moodle platform itself, it links to the platform that we'll be using for this week. And so it's the OpenScienceLab platform.
You have last year's syllabus up.
Oh, that's the wrong syllabus.
Not that, well.
This is the one. Here we go. Sorry about that. So in several places, you see links to the OpenScienceLab platform. So this is, for instance, in the pre-course content, there's link to OpenScienceLab. So if you find one of those, you can click that link, and it gets you to a website that should look like this. So please go to that platform through the syllabus. The link, let's see, can I put that in chat? No, we don't have chat. Can I put that in Q&A? Let's see, where's the Q&A?
I think we can put stuff in chat.
We can put stuff in chat. Okay.
But I don't think other people can.
So you should see a chat message that has the link now. And so please all go to that website. And you can also give me a thumbs up, so you can start practicing your thumbs up and your hands up options to show us whether you arrived. So this is the OpenScienceLab platform. It's the main portal where you land to log into different deployments. So you see that when I scroll down, that in my case, I have two different deployments that I have access to. One of them is the OpenScienceLab ASF deployment. But more importantly, if I scroll down, I have the 2025 EarthScope InSAR workshop deployment that I have access to. This is the one that we'll be using for this class. So please make sure that you all have access to this deployment down here. You see a little EarthScope logo as part of the deployment. If you do not currently have access to this, please go to Slack. And on the Slack channel, post a question. A lot of you have done so, and tag Eric Lundell and Dylan Palmieri on Slack if you don't have access to this deployment, and say things like, "Hey Eric, hey Dylan, I currently do not have access to the EarthScope InSAR deployment," and they will hook you up and get you fixed up. If you do that, and if you don't currently have access, also please provide your username that you used on OSL so that they can connect your username to the class. Okay, so once you're there, there is then a button down here that says "Go to Lab," and you can click that to start that particular lab up. So in my case, I already have a server up, so I'm going to start my server real quick. So you should see then a selection of different server options that you can pick from. So when you click on that "Go to Lab," you get this selection where we have two different machine sizes that you can use. I would encourage you this time to start the M6A X large instance. This is a machine that guarantees you at least 10 gigabytes of RAM, 16 gigabytes of max RAM, and you have several CPUs that you have access to. On OpenScienceLab, everybody gets 500 gigabytes of storage, and that's independent of the machine size. This storage for the duration of this course is permanent. So if you download some data and work with some data sets for the duration of this course and an additional week afterward, you will have access to all of that data on your hard drive. So select the M6A X large and then click on Start. What then happens is you see a startup screen. So in the background, your machine is getting spun up. This should go fairly quick for mine because I had just shut down my machine, so it's still warmed up. For you, it may take a little bit longer, which is fine. It can take sort of up to 5 minutes the first time you start it. We still have some time until we go to sort of the first lab exercise. So it's not a big problem if it takes a little bit longer. So what happens there is a machine with the characteristics that you selected is going to be created in the Amazon Web Services cloud. Then all the necessary software is being installed on that machine. So the machine is going to come with things like ISCE2 and ISCE3. You will have pre-installed software packages such as MinPy and a variety of different Python packages. What also happens in the background is we pull all of the content for this class into the instance from GitHub. So we have a GitHub repository that is being automatically cloned into your instance. Every time you restart your machine, we'll be fetching the latest code from GitHub. So we may actually, a few times during this week, ask you to restart your machine to make sure you have the latest and greatest code available on GitHub, from GitHub and in your machine. While this is starting up, real quick, on the Moodle platform, We did have some pre-course content that we've already gone through. One of them was the introduction to the platform. There was an OSL intro that we've done earlier this week. And Melissa, have we added in the
You click on that link.
for this?
Yeah, it says where it says click on OSL intro recording. That should take them directly to the YouTube video.
Oh, here we go. Yeah, so if you click on that, you get to the recording from that session. So I'm going to stop this real quick. But you see,
Good to
see
see
us on
me
the
and
screen.
you. Yeah. Hey.
And so you can look through that one more time. This is a great face that I'm showing here. Awesome. And you can watch that recording again.
An account or
Okay.
It's also
So my
linked in the
machine
syllabus.
is now still spinning up. Let's see if you can give me a thumbs up for folks that already have the machine up. You can show that with a thumbs up. I see there's a few of you that are already online and ready to go. So I can wait for that for just another minute while mine is spinning up to show you what these Jupyter notebooks look like. And again, were there any questions so far in chat or in Q&A?
Only about getting access.
Okay. And yeah, so please post on Slack, and then Eric and Dylan and maybe Alex are going to chime in and help you out. And again, there's a little bit more time because Gareth is going to do a presentation first before we need OpenScienceLab. So if you don't have access yet, not quite a reason to panic quite yet. So, you know, you see here some messages on the screen, and there's an event log behind it. It basically looks for already running instances. We have shared instances, so there's always, I think, up to 4 people on one instance to share resources. If you ended up being one that got put on a machine that's already running, the startup is fairly quick and fast. If all of the machines were already full and it needed to start a new machine, it can take a little bit longer. And so here it says it's pulling the image. So it's pulling the Docker image for the instance. And then at the very end, now it's starting the container. And then at the very end, it pulls from GitHub, and then we're up and running.
Hey.
Other questions? Are we waiting?
There's somebody reports that they are having trouble starting the small server. And
okay,
really, I think there's no reason to start the small server because we can need eventually, or tomorrow, you will benefit from having more processing power. So might as well go for the big one.
Yeah, so in theory today, I think the smaller server is sufficient. But if you have issues starting that, you can just hop on the larger one. And so, sorry, I thought that this would go really fast because I just shut it down. But somebody took my spot and dumped me onto a different machine.
You can't just tell everyone to start up their servers and then get all complainy when someone starts up their server.
That's right. Yeah, so that gives you a little bit of a preview that can take a little bit longer. So that's one of the reasons why we'll ask you every day to, before we go to the labs, to warm up your machines and start your machines so that you're ready to go when the labs are coming up.
Yeah, and one other benefit of doing that, starting up your server at the start of the day, is that it will pull the latest versions of all the notebooks. And we did do a lot of fixing over the weekend of some of those things.
Yeah, and let me actually show you real quick the GitHub repository. So all of the code connected to this week And to this course, they are exposed at a GitHub organization that's called ISCE+. So you can go there and you can clone that code locally. We have different repositories within that organization. We have the pre-2025, which contains last year's code. And then we have the 25 ISCE+ course, which contains this year's code. And as we go forward in years, we'll have more of those repositories available. And so this is the one. 2025 ISCE+ is the repository that's being cloned into OpenScienceLab. And then next week, once the course is over, you can also clone, of course, this content to your local machine. But for this week, we encourage you to, or we actually insist that you use OpenScienceLab as a platform, because we have about 150 people in the course, and OpenScienceLab ensures that everybody has the exact same installation. So if there are issues with the code, we know then that everybody's instance has the same problem, and we only have to debug stuff once and not 150 times. So this lets us focus on the content rather than installations. And now my machine is up. So once your machine is up, you should see something show up that's similar to what you see on the screen. The important parts are this main interface here. The main part of the interface is the one where you will do most of your work. This is where your notebooks are being opened in, and where you will run the notebooks. On the left-hand side, it shows you the content of your machine, of your instance. You should see 3 different folders here. I have 4 because I did some debugging down here in the temp folder. But the main folder we'll need is the 2025 ISCE+ folder, which contains, if you double-click it, the identical content that you also find on GitHub. And so we have different subfolders there that are labeled 0.1, 0.2, and then 1.0, 1.1, and so on. The first of those numbers is the day of the course. So today is the first day of the course. So all of the stuff that's starting with 1 point is what we'll go through today. So we'll go through 4 different folders today. We already did the introduction. We are currently going through the recap of OSL. And then next we'll go into geophysical modeling. And if you double click one of those, so if you, for instance, go into 1.2, there you see there's a variety of content in that folder. There's a PowerPoint slide deck that Gareth is going to go through. And then later we'll go through that this notebook here. So you can so we'll mostly go through Jupyter notebooks. You can identify Jupyter notebooks by the extension IPYNB, which stands for IPython notebook. And also you can identify them by sort of a little bookmark icon in the very beginning of it. And if you double click one of those, you see what these notebooks look like. They are a mix of so-called markdown cells, which are cells that contain text and graphics and equations. They are really there to guide you through the workflow. And they are mixed in. There are code cells. You can see some code cells down here. Those are executable code. In our case, all of these code cells are running Python code. But in theory, you can build and work with notebooks that support a variety of different kernels, C kernels or R kernels, or even Octave or similar things. In our case, all of the kernels that we'll be using in all of the notebooks, they are based on Python code. These notebooks need a kernel to run into. We'll mostly use the Earthscope InSAR kernel. As you see up here in this little box, we'll use the Earthscope SAR InSAR kernel for most of this. For most of this week. So Earthscope InSAR, and unless you're instructed otherwise, there might be 1 or 2 notebooks where we use a different kernel. This kernel is pre-built, so that comes with your installation. But later, for one of the other notebooks, we'll show you how you can build your own kernel. I also demonstrated this in the pre-course OpenScienceLab introduction. So if you go to that video that I showed you earlier, there are some instructions on how to build a kernel. And we'll go through this particular notebook later today. And unless there are additional questions, I think I would hand it back to Gareth.
Yeah, you might want to show them just right now whilst you have that up. The PDF document is the slides I'm just about to present.
Yeah, so
you double click on, you can
follow
double
along with Gareth on the PDF document,
and you can double click on it on the left, and it will appear
right
on the right.
So if you double click that, the PDF is opening up on OpenScienceLab, and if you want, you can follow along with Gareth through those slides.
And you can also, I think, if you right click on it, you can download
them, right? Yeah, yeah. So all of these things you can download to your local machine. You can right click, and there's an option to download them. You can also, if you want to download lots of different files, one recommendation is to go to the launcher and open a terminal. And then in that terminal, zip up the files that you want to download into a single zip file, and then download that zip file. It turns out that you can't download several files at once. It's easier to zip up the files and then download the zip file for convenience and speed. But yes, we'll get back to the notebook shortly. If you have OpenScienceLab up, please double click on the PDF. And with that, I would hand it over to Gareth once I figured out how to unshare, and let him go through the first presentation.
Super. Right, I'm going to share my screen and maybe minimize the Q&A. So someone else can answer the questions. I'm just going to focus on my slides. Okay, so I'm going to give a brief introduction to geophysical modeling of geodetic data. This you could consider maybe the end point of end goal of the course. You want to be in a position to do something with data that has some scientific meaning potentially, or some physical meaning. I have to click on my screen once. So what do I mean by geophysical modeling? I mean that we can produce models, computational models that have some kind of representation of real Earth processes. The earthquake cycle is shown on the left as one example of that, where you might have, say, an earthquake that causes surface deformation. You might have a continuing slip of the fault that follows the earthquake that we call afterslip, and maybe also viscous relaxation in the crust beneath the earthquake. These processes in general are referred to collectively as post-seismic deformation processes. There may also be some movement of fluids in the crust that is induced by the earthquake that also has some response that is time dependent following the earthquake. In volcanic magmatic systems, you might have dikes that intrude and magma chambers that drain. So you might start with accumulation of magma in a magma chamber, which then is evacuated as a dike intrusion starts, and then that dike might propagate to the surface and cause a volcanic eruption. And all of these processes can be modeled and have predictable surface deformation that you can use to understand the process. And then there's also on the right here represented phenomena associated with ice sheets. So loading of the crust by ice, and then once the ice melts, there is an unloading phase, and both of those cause predictable deformation. So the down warping and bulging of the lithosphere, followed by kind of the unbending and unbulging there. So we can study the processes here using geodetic data, and we can use our models to try and interpret what's going on. Of course, the geodetic data that we are going to be talking about this week is InSAR, radar from satellites, mostly, sometimes from planes, that allows us to measure how the ground moves. There are other types of geodetic data that we won't talk about but if you want to take other courses from EarthScope, you might learn about. So in the center here is GNSS data, just showing the vertical component of motion of a whole load of stations across the Western United States. I think this is the unloading of the crust following drought. And on the right is LiDAR from an earthquake that happened in Mexico. And we can get a very fine scale deformation field, in this case, from differencing point clouds acquired before and after an earthquake. And there are other methods as well. And we will mention at least one more method on this course, which is pixel offset tracking using SAR imagery, which is another way that you can use SAR images to study surface deformation. And we use it particularly to study glaciers. But InSAR is our main business, and so what we're going to show you here is what I'm showing you here is the sort of the very, very basic idea of InSAR, very, very simplified. You have a satellite that flies over the Earth in a fixed orbit that repeats in a fixed amount of time. This particular satellite that's shown here is ERS-1, which is a very old satellite now, but it was really fantastic when I was a graduate student. It's one of the ones that we had available to us then. It had a 35-day repeat, which is considerably longer than modern satellites. But the basic idea is the satellite emits a pulse of microwave radiation as radar. It transmits it to the ground, and at an angle. I should say the satellite in this particular case is flying into the screen, and the radar is pointing to the right. And it emits this pulse of radar from its right-hand side to the ground that gets scattered off the ground, and some of the radar goes back to the satellite. And it measures the amplitude and phase of that radar. The amplitude is related to how bright the backscatter is, which is related to how rough the ground is, or whether the ground is sloping towards or away from the satellite. Typically, the more it tilts towards the satellite, the brighter the response will be. But it also records the phase, and the phase is as a function of the distance between the satellite and the ground. And in practice, the wavelength is so much shorter than the distance between the satellite and the ground. You know, this is of the order of several hundred kilometers, and the wavelength is of the order of a few centimeters. So it's not practical to count all the phase cycles between the satellite and the ground and back again. But if the ground were to move, you can difference the phase between the before the movement and after the movement, and detect just the change that is due to the movement of the ground. That's the kind of the basic principle of InSAR, is we difference the phase, and we can isolate the component of movement which is just related to the movement of the ground. And we use terms like range change to describe the change in distance between the satellite and the ground that we can measure. Typically, if the difference in phase is positive, meaning that the phase measured after the movement is positive, or the difference is positive between after and before, we call that a range increase. The distance between the satellite and the ground has got longer. And similarly, if the ground moves towards the satellite and the distance decreases, we call that a range decrease. You can describe this whole thing as a vector process. So you can imagine some vector of movement of the ground, U, in three components: east component, a north component, and a vertical component. And you could also imagine the vector from the satellite pointing to the ground. We call the pointing vector P. Normally, what we will do is normalize this vector P to give you the unit pointing vector. But anyway, this vector here is dependent on many things that are designed about the mission. The trajectory of the satellite in space, so like how it's flying, and which direction it's flying, and also the design of the radar antenna, like how wide a beam does it have, and what angle is it pointing at. And so, as I say, you can normalize that to give a unit pointing vector, and then the range change, the thing that you actually are detecting with the InSAR, is simply the dot product between the unit pointing vector and the vector displacement of the ground. So if you take the product, the scalar product of these two vectors, the classic form of the scalar product is that you basically multiply the two moduli of these two vectors, the lengths of these two vectors together, times the cosine of the angle between them. And if you draw this as a right angle triangle, you'll see that basically this u times cosine theta, because p is a unit vector, p hat is a unit vector with a length of 1, just gives you this distance here, which is the range change. So even though the ground is moving in has a large displacement in the direction shown here, the range change part, the part that's actually in the direction of the pointing vector, is only this big. And that's what the InSAR would measure. If you were pointing in the same direction as the pointing vector, you would obviously measure a much larger displacement with the InSAR. So there's always this geometrical effect that gets bundled into the InSAR measurement that you have to account for the pointing vector of the satellite. One thing to point out is that sign conventions there is no real standard sign convention for InSAR deformation. Some people report the range change, which is what I've just shown you. If you're thinking about distances between the satellite and the ground changing, that's range change. But some people use another convention, which I call ground displacement, which is, instead of positive being movement down, because you're considering the distance, in ground displacement, you would consider a movement of the ground up as positive. It makes more sense, I think, maybe to earth scientists for that sign convention, whereas the other one is more something that makes sense to radar engineers, perhaps. But that means that some people report positive displacements as downward and some report them as upward. And the only way that you're going to know is if they tell you somewhere in a figure or in metadata of the sign convention. So just be aware that might be the case. Check whether your interferograms are in range change or ground displacement, and check the pointing vectors if they provide them to you and whether they make sense. Typically, the pointing vectors should also include that sign convention. If you're making an interferogram in the ICE processing software, you have to choose two images and choose which one is called the reference image and which one is called the secondary image. The reference image, the secondary image is the one that dictates basically the sign of the deformation. If the reference image comes first and the secondary image comes second, then when you difference the phase of those two images, you get range change. If it's the other way around, your interferograms will be in terms of ground displacement. Be aware, and we will try to make that make that clear to you, which of the two sign conventions our data are in when you're looking at them. And if Franz doesn't do that in the next exercise, tell him or ask him.
Funny, I just posted that we'll talk about those conventions.
Excellent.
So it's in chat.
Excellent. Okay, so when it comes to modeling the data, what you're trying to do is to find a representation of the deformation pattern and then project it into the radar line of sight. So what we have here is a forward model, which is to say we have chosen a series of model parameters that describe an earthquake. For those of you who are geologists, you might have heard of things like strike and dip of faults. Strike is the orientation of the fault, and the dip is the angle that it's inclined at. Where 90 is vertical and 0 is horizontal, and the rake is a third parameter which describes the direction that the fault moved in, and minus 90 is pure normal fault slip. For those of you who know what that means, anyway, you can take those numbers and you can produce a deformation pattern, and then you can project it into line of sight, and this is what it looks like. And these are the radar fringes that show this, that are effectively contours of movement of the ground. Remember that phase is cyclical, so phase change is also cyclical, which means you have to go through a process that we call unwrapping to actually convert these sequential fringes into actual continuous movement. And we will do some of that unwrapping later on today in our little exercise of interferogram interpretation.
There's a question. Oh,
yeah.
so a question in Q&A, and maybe Scott could help answer that, is what is the sign convention in case of time series INSAR, or particularly PS INSAR analysis? And I think it's going to depend on
Whoever makes the time series. Yes.
whoever makes the time series, and whether, as Gareth was saying, your results is in line of sight ground displacement or in range displacement. But maybe Scott can comment on what Opera is doing.
Yep. No, that your answer is what I would say, that there's not a convention for time series versus PS versus anything. It's, yeah, it starts from the processor and how you make the interferograms. Yeah, the Opera ones try to follow the ISCE convention, where your interferograms are in the complex domain reference times secondary conjugate, and then once you convert it to ground displacement, then you have the positive, meaning moving towards the satellite platform. So that combining two moving towards positive numbers leads to a positive uplift.
Great. Thank you.
So the important thing is that you know what your processor is doing. What's typically the case is that the processors you're using are internally consistent. So it's important that they themselves are consistent throughout. And once you have the final geocoded product, there's usually a consistent definition that it's in line of sight displacement. So as long as you're aware what happens in between, and as long as you can rely on a processor that is internally consistent, your results should come out the right way.
Cool. Yeah, the other thing that I was going to say here is that you can represent this model as a very abstracted kind of function, where D, the output of the model, is the simulated data that's plotted here. G is the theory that we use to produce the model, and M is a series of parameters, numbers that describe certain aspects of the fault. And so here, the strike, the dip, and the rake, plus also the length of the fault, the depth of the fault, the width of the fault, and the location of the fault. And if you have these and you have the appropriate theory, you can make something that looks like an interferogram of an earthquake. There's also inverse modeling, which basically does the thing in reverse. You start with data, actual measured data. You produce a model that tries to fit the data that you have. And the goal would be to minimize what we call the residual, which is the difference between the data and the model. So if you subtract the model from the data, this is what you get left. Ideally, the whole thing would be sort of uniform flat green. That would mean you've completely fitted the data with your model. In practice, there will always be some complexities that you struggle to fit. This is a particularly simple model with only the fault being represented as a single rectangle with slip, which is uniform on the whole thing. So it just moved as one entity, one distance, which is probably not realistic in detail, but is a fairly good approximation to start off with. And in this case, you would represent the model equation this way around, where now we have estimated model parameters as the output and some inverse operator, something that represents the process of trying to fit the data, and the input to this model is the data. As you'll see, this is not every single pixel in an interferogram. This is about 200 pixels or 200 data points sampled from the interferogram. And the reason that we don't show every single pixel or try to model every single pixel is it takes a lot of computation to do that. And you can still get good results by what we call downsampling the data. And we will talk about downsampling tomorrow. One thing to point out, nearly everything that we're going to show you in the modeling sense this week is going to be an elastic model. That is because the surface part of the crust behaves like an elastic solid. And of course, our measurements are all filtered through this elastic material that we live and work upon. We've understood that this was the case since 1906, or just after 1906, when Harry Fielding Reid, who was a surveyor, realized that there was this change in angles between all of his triangulation sites in Northern California following the 1906 earthquake, and he was able to look at both the data that was collected before the earthquake and data that was collected after, and realized that different parts of the crust had moved at different times. Before the earthquake, the far field had moved, so you can imagine the Pacific plate on the left and the North American plate on the right. The Pacific plate was slowly moving and causing the crust to bend, but the fault was locked by friction. And then when the earthquake happened, basically the bending had stored a lot of elastic strain in the crust, and that elastic strain was released along the fault, and suddenly then the fault caught up with where the far field had moved to, and that displacement was predictable by elastic theory. So this was a big realization, and now we have lots of codes that can actually calculate elastic displacements of the surface under different conditions. Most of these are what we call half-space models, where you treat the Earth as basically an infinite or semi-infinite elastic solid. You can imagine a cube that went on forever that had beneath it elastic material and above it no material. That's different from a full space, which would just be material everywhere, and you never see the surface of it. The surface effects are actually important to consider. They change the deformation pattern a lot, so that's why this is our sort of simplest model that we often use to study Earth deformation, because obviously deformation happens only in the ground; it doesn't happen above the ground. And we often also assume things like the elastic solid itself is isotropic, which means it has no difference in elastic behavior with different directions or different depths. It is just the same elastic strength everywhere. And inside that half space, you can embed structures that you want to measure movement of. So, for example, a fault would be represented as a rectangle in this. And you can embed other things like volcanic sources as well. The simplest of all the elastic models is a volcanic source. It's the one that Franz will show you in the next exercise. It's called the Mogi source, or the Mogi model. It's good for volume or pressure changes in a sphere. And this is a good first approximation to what a magma chamber in a volcano might do. It's described by these two equations, which is really easy to code up. Whoops, as you will see in a minute. It's very easy to evaluate this model, and it relates the volume change in the magma chamber here to the vertical and horizontal displacements of the surface. The vertical is always, upwards or downwards depending on the volume change. If the volume increases, you will get a movement upwards. If the volume decreases, it will subside. And the horizontal deformation is radial, so it's symmetric in all directions. Again, with an increase in volume or an increase in pressure, the movement of the surface will be away from the point above the magma or the spherical source, and if it's negative, it will be a contraction. It will move towards that area, and it's as long as you're within certain rules of thumb as to the location and the size of the movement of this source, then this works quite well. It does make certain simplifying assumptions which may not always be true. For one thing, the source radius has to be a lot larger than the depth for this to work well. You're assuming that the magma is incompressible, because if it did compress internally, then that you wouldn't get such a big displacement of the stuff around it. And again, it requires the crust to be isotropic and a half space. We know that particularly in volcanoes, that's not true, because the volcano is actually has a topographic expression above the magma chamber usually. The equivalent simple model for faulting, and also useful for things like magmatic dikes, is the Okada model. This represents the source as a rectangle, And you can have displacement in the plane of the rectangle, in the direction of what we would call strike, that would be strike slip, in the direction of dip, which would be dip slip. And the third possible component would be a component of opening or closing, which would be the dike-like behavior that you might want to model in a magmatic system. This is a much more complicated set of equations than the Mogi source, but it's still what we call analytical, which means that someone actually, well, Okada himself, actually went through and integrated all the equations correctly and solved them. The reason that he gets all the credit is that he was the first person to do this without making any numerical or calculus mistakes. Basically, it was a very complicated set of things to integrate, and he did it first. He was the first one to do it correctly. On the plus side, it's really fast because you just have to plug in numbers into equations and you get an answer. That's what we call an analytical solution. But on the downside, again, it's not. It makes the assumptions that are maybe not realistic. The surface is flat, that the materials all the same properties, and of course rectangles are kind of complicated. If your fault is actually a bit more complex and has some curvature or some bending to it, rectangles are not very good at representing that. There is like a thing you can do if you really want to model all the things and do them accurately. Then you can use finite element models to produce your displacement fields. Here you have control over everything. You can have a realistic surface. This is an earthquake that happened in Nepal, and we just cut away the ground to show you where we put our fault. But like the surface was mountainous, so there's all this topography here. You can also change the material properties with every element. So this domain of material is sampled or meshed with 7 million tetrahedra. So 7 million little pyramids in the ground, and you could choose the material properties of every single one of those if you wanted to, or you could layer it, or you could do whatever. You can also include more than just elasticity in the model if you wanted. You could add viscous deformation to it. So this is kind of the other end member case where we are actually modeling everything. We can model every effect, but the downside of this kind of model is it's extremely slow and expensive to model. Setting up the model is a lot of effort, and then computing the model is even more, takes a long computation time. So often you can this type of model is great because you can gain insights that you wouldn't get from say an Okada model of an earthquake. So this is a mesh that my colleague Christos Kyriakopoulos evaluated for the Gorkha earthquake in Nepal, which is something that we had InSAR data for. And one of the things we saw in the displacement pattern, which was really interesting, is that you can see that these are displacements color coded. And now we're imaging not only the displacements of the surface, but the displacements of the interior of the model as well, which is interesting. And what you see is that there are a series of ridges that are perpendicular to the fault. The fault's down here. At the surface, these are the tops of ridges that are perpendicular to the front of the topography as well. The structural trend in the mountains, with the higher mountains being over here and the lower mountains down here. But if you looked at the displacements along the surface here, you would see that basically it's oscillating between higher displacements and lower displacements. Higher displacements in the valleys and lower displacements on the ridges. And that's basically because your deformation decays with distance from the fault. And if you're on top of one of these ridges, you're actually further away from the fault vertically than if you're down here. And you wouldn't get that insight from a half space model where the surface was completely flat. So that there is some value to these more complex models. It's just that it's not tractable to model every single adjustment to a fault model this way. You have to kind of know where your fault is before you calculate one of these. In between, there are other modeling codes, and I'm not going to go deeply into this, but there are models called boundary element models, which model displacements or strains on surfaces. So instead of modeling volumes, which is what a finite element model does, like we know everything that's going on in the interior of this model as well as what's going on the surface. A boundary element model, you would just be modeling the fault or your dike or your magma source, whatever it is, and you would also be modeling another surface, which would be the Earth surface, and then ignoring all the material in the interior. This, of course, goes a lot faster than a finite element model, and allows you, and because of the way that the surfaces can be described, they're often described by triangulate meshes of triangles. You can make more complicated things this way, and that's good. It's good for realistic complexity, but these are still very, very slow compared to, say, Okada or Mogi models, and they generally don't allow you sort of complexity and material properties, which we know exists. But anyway, this is a good kind of compromise in many circumstances. I mentioned already that we'll be talking about or demonstrating data downsampling tomorrow. The idea that you can represent an interferogram with all its displacements. This here is an unwrapped interferogram of an earthquake in Turkey, showing different displacements color-coded, positive and negative, and you can see that the data is represented as a series of squares. Each of these is an average of the displacements in this box. This type of sampling is called quadtree sampling. The essential idea is that you define an area and you calculate the variance of the data in that area. And if the variance is above some threshold, if there's a lot of variation in the phase in that area, in the interferogram displacements, then you divide that area into 4 and you try again. So what happens as you sort of go through iterations of this is that places where you have lots of change in the surface displacements tend to get sampled more finely, and things that have very, very uniform displacements tend to have very, very coarse sampling. And it's a good way of sort of reducing an interferogram to its essential information. That's shown here. You have a lot more stuff going on here, so we're going to sample it much more densely, and over here nothing is going on, so we can sample it coarsely. And the advantage of this is that you only have to model then with your modeling code this 200 or so points instead of the several million pixels that the interferogram would have otherwise. And there's more or less a one-to-one increase. Well, there's a linear increase in the computation time with the number of data points that you have. So if you reduce that, you reduce the computation time, which is great. And when we talk about modeling styles, there are, and it's specifically inverse modeling styles, where we're trying to take our sample data and turn it into a model. There are 2 philosophies that we can adopt in most modeling cases. There's the linear case and the nonlinear case. And this is an example of linear inverse modeling here, which is trying to solve for the amount of slip on a fault that moved in an earthquake. And there is a direct linear relationship between the amount of slip that you had in the earthquake and the amount of displacement you get at the surface in this case. So if you have the same fault with the same depth and the same length, and all that you're changing is the slip, then if you have a slip of 0.5 meter, you get this displacement pattern. If you have a slip of 1 meter, you get this displacement pattern. But you can see, for example, that the maximum displacement in the model is always in the same place. It's in this location here on the south side of the fault, and it's at this location here on the north side of the fault. You keep scaling up the slip. You can halve it or double it, but all you really end up doing is doubling the displacement. This linear relationship means that you can use much more efficient mathematical methods to solve for the amount of slip. In this particular model, m is the slip, the model parameter that you're solving for, and it's a linear product between the a matrix of Green's functions, which is a description of the model. Basically, you calculate a forward model for all the parts of the fault that you're interested in, and M is the slip. So you can see because of this proportionality, if you doubled the values of M, you would double the values of D. In other words, you would double the amount of slip that displacement that happens of the surface, which is what D represents here, is the surface displacement. And you can do some matrix math, and you can rearrange this equation such that you get the slip as a function of the data, if you want, the observed displacements. So this is a fast method, and you will be able to compute this very, very quickly. The nonlinear case is a bit more complicated, unfortunately. And that's because really it's only the slip parameter in a fault model that is linear. Everything else has a nonlinear relationship with displacement. So if you change the position of the fault, that changes the displacement of every point on the surface in a way that's not predictable. If you change the dimensions of the fault, the same. If you change the orientation of the fault, the same. I've shown you just an example here of what happens if you take the central depth of the fault and you move it downwards. So you start a model which is at 6 kilometers, which is, I think, the same as this one here. And what happens if you bury this fault more? Well, a few things. One is that surface displacements get smaller, and that's not surprising because your fault is now further away from the Earth's surface. But you can also see that whereas before the maximum displacements always stayed in the same place when you increased the slip, when you increase the depth, the maximum displacements actually move further away from the fault. So you can see now that this is a greater distance away than this is. And if you go down to 12 kilometers, it's even deeper and even more muted surface deformation field and affects a wider area, but with less displacement. So you can't model this with the simple linear math that you would use for the linear inverse model. Instead, you have to use what we call an optimization approach, which is where you have an algorithm typically which tweaks the model, tweaks a model, a forward model. It calculates what the expected surface displacement would be for a set of different model parameters, and then tweaks those parameters and sees which ones lead to an improved fit to the data. And so there's some kind of systematic manipulation of your model parameters until you get a model that somewhat fits the data. But this requires lots and lots of trial and error, basically, of the modeling algorithm. There is not just a single answer that can fit the data as well. There's often what we call non-uniqueness to the model. Yeah, whereas the other one, you could get the answer in one run. In this case, you would probably run the model thousands to tens of thousands of times before you find something that fits. And then you might want to try again because the model answer is non-unique, and you might need to try it several times to find a better answer. And we will go into a bit of this nonlinear inverse modeling tomorrow, and we will do some of the other type today. Well, actually, the model we're going to do today is also a nonlinear model, but a simpler one. And I think that's my last slide. Yeah. So I've seen questions popping off in the Q&A.
There were a few questions. One maybe you can address is you talked early on about long wavelength and short wavelength displacement. And, some wanted you to elaborate a bit more what you mean by that. And I didn't want to interrupt you.
Was that with relation to the buried fault thing, or?
I think that was probably early on about interferograms.
Oh, well, yes. So you have to be careful what you mean by wavelength, because you can talk about the wavelength of an Earth process versus the wavelength of the radar. Those are two distinct things to consider. probably was talking about the wavelength of displacement in the sense of this feature is seen over a large area on the Earth's surface, which will be a long wavelength deformation. But yes, a long radar wavelength will give you a different interference pattern in an interferogram than a short one. You would get a lot more fringes for a short radar wavelength, because each fringe you see in your interferogram represents a movement of half the radar wavelength of the ground towards or away from the satellite, which I did not mention before. But Anne will, I assume, talk about that a lot more this afternoon.
Yeah, and spatially speaking, you could imagine that if you have a landslide motion, which is quite local, that'd be a spatially small, short wavelength kind of displacement. While if you'd had sort of interseismic displacement, which can be very large scale, that would be a long wavelength type of displacement, spatially speaking.
Yeah, so that case of the Pacific plate and the North American plate moving, that's manifest over a zone that's 100 kilometers wide or something like that. Whereas the earthquake deformation was focused on the fault itself.
Alireza, does this answer your question? And if you can also speak up. But,
that's right. You have the power to unmute if you so wish.
There's also a question that just popped up. So Alireza has a follow-up. So is it a matter of spatial extent rather than magnitude?
Yes.
Yes, even though they are somewhat linked, larger magnitude earthquakes.
Yes, sometimes if you have a process which is deep, then the deeper the process occurs, the larger the wavelength of the deformation at the surface. It will affect a larger area, but also its magnitude will be decreased the deeper it goes. So as Franz says, they're sometimes linked.
And then there's a question about slip also varies along the fault at different locations. And if that's the case, can nonlinear modeling help address that?
Usually, actually, linear modeling helps you address that, because you can divide your fault up into more rectangles, and you can have different slip on each one. That's still a fairly efficient way of modeling. When you have to have more than one rectangle in a non-linear model, you're increasing the number of parameters by a lot, and the computation time is significantly slower for two faults than it is for one.
Excellent.
I actually have a paper on that if you want to talk about it sometime.
Should put that in chat.
Yeah.
Slack. Great. Other questions for Gareth? So one of the goals of this early phase, there's a hand up. Was there a hand up? It came and went.
Oh yeah, you were talking, so yeah, I didn't want to interrupt.
Go ahead. No, go ahead.
So and it's something that Gareth just mentioned, and something that I read somewhere. So you are able to detect half of the wavelength on displacement. And I got this question several times. So how do you detect millimeter size detection if what you can detect is on the order of 2.5 centimeters or something like that?
Well, okay. So that's the difference between two fringes, but you can still see changes that are smaller than a whole fringe. You sometimes see like yeah, and we have that whole you can divide that whole color scheme between like blue and red on those wrapped interferograms into, well, you could probably divide it into 10 divisions that you could clearly make out, and possibly even more than that. So 10 divisions between of 2.8 centimeters would be like 3 millimeters. You could potentially identify that.
Yes, and I'm sure Anne will talk about this more when she talks about ISCE and InSAR Theory after the break today. There's a question: if we have two sources, can we separate them basically, or measure them both?
You can. Sometimes they interfere with each other, or they trade off against each other. It's very hard to uniquely determine two sources in the same place, because some of the displacement from one might add or can interfere with the displacement from the other. But you in theory you can, yes.
Yeah, and so in sort of volcano hazard analysis, that can happen a lot, was you may have sort of magma move around between two different sources. They may ascend from a deeper source to a shallower source, and what you see in the interferogram may be a combination of the deflation of the deeper source and an inflation of a shallower source. So many modeling efforts are set up trying to combine this displacements that are forecasted by more than one source.
And the more data you have, the more constraints you can apply. So if you had some evidence from seismology or something about the location of your deep source, you might be able to constrain that part of the model a little better.
And also, I think we go through this at some point in this course. It can also help you if you have multi-geometry InSAR data, like ascending and descending data, to really see the difference between a single source deforming and a combination of multiple sources deforming. We had and I can also post that in Slack later today, we had a case in Alaska of a volcanic deformation that in a single geometry looked like a single MOGI source. But then once you had ascending and descending available, it became clear that a single source is not sufficient to explain the displacement we saw. And we needed to model it using a combination of sources. So having multiple geometries available also from a InSAR data perspective can help you get to the bottom of the geophysics that's driving the displacement.
There is a question about, does the deflation and dike intrusion give you the lava flow volume, or maybe not the volume of the lava flow, but the volume of the lava in the dike? I don't know. This is the sort of question that could be answered in the next session, maybe.
Yeah, and Eric Fielding may also be able to chime in. How do you separate groundwater extraction signals from a volcanic signal? Do you want to?
Well, hopefully they're spatially distinct, but they would look awfully similar in some ways. I think the pattern would be slightly different, and the localness of the deformation would also give you a clue. You're right there, Melissa?
Yeah, we should probably, so thank you for all these questions. Those are great. What I suggest is, in the interest of time, please all make sure that you have your OpenScienceLab instance started up. We'll go through a little exercise real quick of doing a very simplified version of model inversion, where we take some geodetic data, which in this case we have from InSAR, and try to use those to understand the parameters of a geophysical model under a volcano. We'll use a simplified MOGI model for this, and we'll do that in OpenScienceLab. So please make sure your machines are up and running. I'm going to share my screen in a sec. And in the meantime, if you have more questions about modeling, please keep them coming. And the team, Gareth and etc., will be answering those as we go through the exercise. So please go to OpenScienceLab. I'm going to put the link in chat one more time for folks that are not there yet. Most of you are already up and running. We verified that earlier. Oh, I'm in the wrong chat. Give me a sec. How do I get out of this? Can somebody share the OpenScienceLab chat? I have like some sort of a private chat up that I don't know how to get out of. Stupid new Zoom window. Okay. So I'm going to share my screen. You all should be ready with your OpenScienceLab instance. Please give me a thumbs up when you're all ready. So exercise your thumbs up skills. So I see people coming in. If you still have issues accessing OpenScienceLab, most of you, I think, have been approved now. Eric was great going through the list on Slack and approving most of you. If you still have issues accessing it, please post on Slack, and Eric will jump on it and give you access. Okay, so what we'll be doing now is we'll basically try to, for the first time, exercise what Gareth just talked about, to combine geodesy, which we get from InSAR. So what InSAR will give us is a measurement of displacement, which is a geodetic measurement, but it doesn't tell us right away what geophysically happened to cause this kind of displacement. So we'll combine geodetic measurements we have from InSAR with a geophysical model, in this case the MOGI model that Gareth showed earlier today. So if you are on OpenScienceLab, please go to the 2025 ISCE Plus folder, and in that folder, scroll down to section 1.2, which is the geophysical modeling section. So the one that's highlighted on my screen now. You guys should all see my OpenScienceLab screen. And then go into that folder. And in that folder, we have a Jupyter notebook that's called Earthscope InSAR Geophysical Modeling. Geophysical Modeling Homework 1. So that's the first exercise we'll be doing. And please double click that and open that notebook. And you should see a notebook that looks similar to what you see on the screen here. So you should have a little banner on top, and it should be Homework 1, Volcano Source Modeling using InSAR. And again, give me all a thumbs up once you're ready to go. Okay, I see lots of thumbs up. Excellent. So the goal of this exercise is described in this top header. Is we be using a MOGI source model to describe displacements related with an inflationary period at a volcano called Okmok. Okmok is a volcano in Alaska in the Aleutian chain, and so we'll look at that one specifically. We'll talk about that here in a sec. We'll be using an approach to estimate the best variables for this source model using a grid search approach, which is sort of a simplified way of inverting a geophysical model. It's sort of a pseudo-inverse of the MOGI source model. We'll go through that here in a sec, but basically it's a trial and error approach where we vary the free unknown parameters of the MOGI source model. We create displacements using this MOGI source model, and we pick the model combination whose forward model displacement is closest to the displacements we have actually observed. So we try to solve for the best fitting source parameters using a grid search approach. There's a red box here that says like this notebook includes 3 homework assignments that are to be answered on the Moodle platform. So if you go to the Moodle platform, let me see if I can move this over to the other browser real quick. See if I have Moodle up still. I used to. Oh, I don't have it up quite now, but if you go to the Moodle platform, there is a homework assignment where there are questions for you to address, and you need to run this notebook to be able to answer the questions on Moodle. So all the questions are to be answered on the Moodle platform. Okay, so now we are ready to go. You see in this notebook, you have these text entries here in so-called markdown cells. You see that this particular cell is a markdown cell, first of all, because you see graphics and text, but it also shows you here in this drop-down menu that this one is labeled as a markdown cell. So markdown is used to just convey information about the code and help you walk through a certain exercise and data recipe with instructions. But if we scroll down here, then you have the first code cells that we have to execute. And so the first two, just make sure that you're running in the correct kernel. So if you run those two code cells, you can either do that by clicking on it and clicking on that sideways triangle symbol up here in the menu. Or what I tend to do is I run the code cells by going to Shift Enter on my keyboard. Shift Enter exercises a code cell and then jumps to the next code cell and lets me then run the next code cell right away. So those first two code cells, they make sure that you're running in the right kernel. We are expecting this to run in the Earthscope InSAR kernel. I am set to the Earthscope InSAR kernel, and so should you. If this kernel is not automatically selected, you can click on that little cell up here and then go to the drop-down mode and pick Earthscope InSAR as your kernel, if it's not automatically set this way already. So in my case, there's no complaints. If I was in a different kernel, it will give me some red text here that says like, hey, you're running in the wrong kernel, please switch your kernel. So now that we are in the right Python environment, we can then go through the essential part of this particular notebook. You'll see that this notebook is built in a way as most notebooks are. It starts with a section that imports the relevant Python packages that we need for this particular case. So you see there's a code cell here that you have to run, where it imports a bunch of libraries. We use the OS Python library, subprocess, matplotlib, numpy, the typical ones that you may have used in the past. I shall say as we go through this notebook that it is essential whenever you run through a notebook that you run them, all the code cells, in the order they are given. So don't skip a code cell, you have to run them all. You can see which code cells are already run because they have a little number in these square brackets on the side. You see here, this particular notebook has the number 5 in it. It means that it's the 5th code cell that I have run in this particular notebook. The latest code cell that I've exercised is the one that has the highest number. If I would rerun this code cell, it will increment this number to the number 6. And so this is then the last code cell I have executed. And so make sure that all of the code cells are run. If you miss a code cell, you may end up with an error message because it can't maybe find a variable that it declared in the code cell that you missed. So the most likely cause of an error is that you skipped a code cell when you went through. Okay, so now we have all our Python libraries run installed, and now we can actually go through the exercise. And so what we do here is we try to model displacements observed at a site called Okmok Volcano in Alaska. You see here in this little map inset where Okmok is located. In this map, you see mainland Alaska up here. You see Kamchatka over here on the eastern side. So this is where this large earthquake occurred just a few days ago, a few weeks ago. And then in between Alaska and Kamchatka is the Aleutian chain. The Aleutian chain is created by the Pacific plate subducting under the American plate up here. And it causes a lot of volcanism on the north side of that subduction zone. And so there are a bunch of islands that are being created. And one of those islands is Unimak Island, which houses Okmok volcano. You see the volcano here. And then also on this little inset on the left-hand side, you see the displacement of Okmok during the relevant periods that we are looking at here. And so those displacements here are measured using campaign GPS stations that are located in several places on the island. You see on the left plot the horizontal motion. Where you see that there's a radial motion away from sort of a central point on Okmok. This is often indicative of sort of a Mogi source inflation, sort of a ball-shaped inflation of the surface. And accordingly, you can also see upward motion. So the horizontal motion shows upward motion that is very large near the center of the island and then diminishes as you go away from the center of the island. The time period we are looking into here is between the year of 2000 and 2002. This is in between two eruptive phases of Okmok. Okmok is very nice for InSAR because it's a very agitated volcano. It tends to deform quite a bit as magma moves around under the surface. So we have a single interferogram we look at here, which is created by ERS-2. ERS-2 was a C-band SAR satellite operated by the European Space Agency that flew sort of around that time. And the interferogram we look at spans a time span of about 2 years, from August 18th of 2000 to July 19th of 2002. And during that phase, there was an inflation at Okmok that we'll be looking at. And so the primary goal of the problem is to estimate the values, the 4 unknowns of the MOGI source model. And we'll get to those unknowns here in a sec, using the observed INSAR-based displacement. And so we start first by running these next code cells in section 2. These code cells are downloading the data, the displacement data, and are preparing it for visualization. So if you run all these code cells in section 2, you can run them all the way through. It first downloads a data set. In this case, we deposited this data set on an Amazon S3 storage device. S3 is Amazon's cloud storage device. And so in this case, we are downloading an unwrapped interferogram created by ERS and spanning these dates that we had mentioned, August 18th of 2000 to July 19th of 2002. The data set is stored as a flat binary file. So in order to interpret this, we need to tell the computer a few things. We need to tell the shape of the data set. So we have about 1,100 samples and 900 lines. And the resolution of this data set is 40 meters. So we have about a 40 by 40 kilometer chunk of data that we'll be looking at. We also tell it how to interpret the phase. And so we give it, it turns out that, and Anne is going to talk about this more, that half a wavelength of displacement causes a full fringe of phase change. And so in this case, this is a C-band satellite. There's about a 5.6 centimeter wavelength. So 2.8 centimeters of displacement would cause one full fringe of phase change. And so 2.8 centimeters here expressed in the form of millimeters. So it's 28.3 millimeters of displacement corresponds to one fringe of phase change. So we tell the system that too, so that we interpret data sets correctly. Then we load our data in, and we scale it into a unit of, in this case, millimeters, by multiplying the unwrapped phase by that half phase variable to interpret the data. We also remove some bad samples. We remove some data points that are not numbers. It turns out that the island, Okmok volcano is on an island. It's surrounded by ocean, and in the ocean, we don't have any coherence. So in order to not get distracted by noise in the ocean, we basically mask out all the incoherent places in this line, and sort of end up with a variable that has all the not numbers removed. And then, so we create the masked variable here that's called observed displacement map _ m, which is the masked variable. Then in section 2.2, we then plot that variable visually. And so if you run through these code cells, what we do here is we create first a folder that's called plots. So all of our graphics are going to be stored in that folder called plots. And then we write a little function. So this is a way of writing a Python function by starting with that def command. We write a function that's called plot model, which takes a file as well as an extent of that file and the resolution of that file to then output a graphic. And so then later we exercise this function. So we now run plot model, without masked displacement map to visualize the observed displacements. So what you see, you should get a graphic here side by side. Hopefully, if you can give me a thumbs up, you should all see this. On the left-hand side of this graphic, you see the unwrapped displacement in units of millimeters. You see here a blue blob in the middle, which indicates that there's displacement. You also see lots of green color. Green color here corresponds to no displacement. And on the right-hand side, you see that same graphic rewrapped into what the original SAR dataset would have looked like. So this is a simulated interferogram rewrapped into 0 to 2 pi of phase change. And you can see that we have a little bit more than one fringe of displacements that occurred over those 2 years. Now, let me ask you a question. And maybe some of you can try to unmute and try to give an answer. Is you see that there is a blue signal here, which is a negative signal on this scale. What do you think this means? Does this mean that the pixels moved further away from the satellite, or did they move closer to the satellite? What does the negative sign here imply? Closer to the satellite or further away? Maybe let's give a thumbs up for folks that think it moved further away from the satellite. Further away, we have 2, 3, let's see, 10 so far. So give it about 15 or so. And now a thumbs up for all the people that think it moved closer to the satellite. Okay. It's about a split vote, so it was about 15. And lots of folks undecided. So this data set is given in range change. So in this case, negative numbers mean that the range has shortened. So these blue pixels, they moved closer to the radar, which is somewhat consistent with what I told you earlier, that this was an inflationary period. So the volcano actually inflated over that time, so the surface rose up mostly. And that shortened the distance to the satellite, and hence in these range change numbers, the numbers are negative. So that's part of the confusing things that Gareth talked about. Here, negative numbers means shortening of the distance between the satellite and the ground. Okay, so these are our observables. So this is what we measured using the satellite. This is our geodesy. Now in section 3, we want to start thinking about connecting these geodetic observations with the geophysics under the surface. And so we make an assumption here. We assume that the displacement we see is caused by a Mogi source inflation. And so as Gareth mentioned, a Mogi source is a small point source under the surface, a spherical source under the surface that was injected with magma, where magma was flowing into, and that injection of magma caused that spherical source to expand. And as that sphere gets larger, from say a ping pong ball to a basketball and so on, that expansion is going to propagate upward and will deform the surface above. How a Mogi source, an inflating Mogi source, deforms the surface is shown in these equations in section 3.1. And so the Mogi source model provides a 3-dimensional surface displacement that's expressed here by the variable u. So that's the thing that's shown here on the left-hand side of this equation. And so it's caused due to an inflating point source that has 4 parameters. And the 4 parameters are the XYZ location of that source under the surface, and the volume change or the change of magma volume in that source. So those are our 4 parameters: XYZ, and volume change V, or more correctly, we should say delta V here, but I'm saying V in this case. And how these parameters are linked to our surface displacement is shown by this equation. So first of all, you see how much displacement we get in a certain pixel depends on the distance of that pixel from the source, expressed here by these Z minus CS, Y minus YS, and X minus XS. So the further away the source is, the less displacement it will experience. And then also you see it here by the radial displacement. So here's the radial displacement between the point on the surface and the center of the source. And so here you see what how this radial displacement is calculated. So the larger this radial displacement, sort of the further away the point, the weaker of a displacement it will see. And you see here that the displacement is in X, Y, and Z, so not only up. So the displacements in up, in X, and in Y are caused by this source. So this model gives you put in with this equation, you could feed the equation with a source location, X, Y, and Z, and a volume change, and it's going to create you an estimate of the three-dimensional surface displacement this particular model would create. So that already puts us in a good place. We can now forward simulate different surface displacements. But because we are looking on the ground with an InSAR system, and InSAR actually does not see three-dimensional displacements, it only sees the line of sight component of this three-dimensional displacement. So it only sees changes of range. What we also need to do, we need to add a second model that describes how a uplift caused by a volcano, here shown by this vector U, is projected into the satellite's line of sight. The line of sight vector is here the L hat vector, and what the satellite actually sees is the projection of U into the line of sight direction, which is this product of U times L hat. And so our observed displacement is this gray vector alpha here. This is the component of the displacement that we actually observe with the interferogram. So we need to add a second model, this set of equations in this block, then take our forward modeled displacement U and project it into the line of sight to simulate the displacement observed by InSAR. So here the displacement of InSAR is the three-dimensional displacement vector projected into the line of sight. Okay, so those two combined allow us then to simulate interferograms by postulating certain MOGI source displacements. And so this next section 3.3 allows us now to create simulated MOGI forward models. And so if you run these next two code cells, those are defining a couple of functions. This first function here called calculate forward model MOGI, that encodes the first set of equations we looked at. So that allows us to calculate a three-dimensional displacement vector based on our four source parameters. And then the second equation allows us then, this second equation is the one that calculates the three-dimensional displacement vectors. And then this first function then projects the three-dimensional displacements into the line of sight. And so once we've defined these functions, we can then exercise them. So we can then, if you run this next code cell, what this next code cell is doing, it is then simulating 9 different forward models and simulate the surface displacement caused by 9 different forward models. And so those forward models have a constant volume change. So we have a volume change of 0.0034, in this case, cubic kilometers. So I should have said that this is in kilometers cubed. So that's the amount of magma that came into that source. And we postulate a certain depth. This depth is given in kilometers. So this source is at a depth of 2.58 kilometers. And then we allow for 9 different combinations of X and Y. So we put the source at these 9 different solutions, three different X locations and 3 different Y locations. And if you run this code cell, you should see this surface displacements that we simulated. Hopefully you got all of this, this graphic. You see sort of the source moving around. So these different solutions put the source into different locations, and you see how the blue displacement blob is moving around as we change the center of the source. As a star, you also see the actual center location of that source. So that gives you a little bit of an idea how changing the source model parameters can change the output of the forward modeled surface displacement. This particular case looks pretty similar to what we actually observed with InSAR. So those source model parameters are pretty close. But you can, if you want, go up and change certain things. I'm going to do something drastic here. And I'm going to make the volume, the source volume, larger by a factor of 10. And I'm going to rerun this cell. And when you do that, you will see that the displacement has gotten much larger. So here by a factor of 10 larger, you see now a huge uplift, or sort of a huge signal that indicates a movement toward the sensor. And you can also see something interesting that you may not have expected. You see a orange blob now, which corresponds not to subsidence, but it corresponds to net increase of distance to the radar. This increase of distance is caused by the fact that when the MOGI source is expanding, it moves pixels both up and to the side. So there's both a horizontal and a vertical motion involved in this MOGI source inflation. And in these orange blobs, the horizontal motion, which in this case is here to the east, the horizontal motion actually outweighs the uplift, and therefore we get a net range increase in these particular areas. So later on, when you get back to this notebook, feel free to play around with these source model parameters, because it gives you a little bit of a feeling how sensitive the forward model is compared to the forward model parameters. And it also gives you an idea of which model parameters may fit your observations well and which model parameters fit the observation poorly. Okay, so you can go through these exercises here on your personal time, and there's going to be a question on Moodle relating to these exercises. Okay, so now we can jump to section 4, where we now try to solve for the inverse model. So what we now try to do is we now try to find the set of MOGI source models, so X, Y, Z, and volume change, that fits our observed displacements the best. And the approach that we'll do is an approach of least squares, which is often a sort of way for us to find the best fitting solution. And so what we are doing is we run a forward model, shown here by GM, and we have our observed displacements. And we define the best set of model parameters as those that minimize the difference between the square of the difference between the modeled displacement and the observed displacement. So we create a model forecast, we subtract the observations, we square the difference between those two, and we sum up those differences. That's the so-called method of least squares. And we define the best fitting set of source parameters as the one that minimizes that least squares difference between the model and the observations. And so technically what we'll do is we'll loop through a set of MOGI source parameters. In our case, we'll change the X and Y parameters. We assume that we know the depth and the volume change, so we only search for X and Y to make things easy. So we loop through combinations of X and Y. For each one of those combinations, we will calculate the forward model. Then we calculate the so-called misfit, so the difference between the observations and the model. and then find at the very end the set of XY parameters that minimizes this misfit. So that's one way of determining the best fitting source parameters from a set of observations. So before we go through this, we'll experiment a little bit with misfit. So if you run this next code cell, what it does, again, it calculates a set of forward models first. And then, so what is this doing here? I thought it would look at misfit. So this is just looking. Oh, this should have shown the misfit between forward model and displacements. I must have pasted the wrong code cell here. So sorry about that. I mislabeled the code cell here. This should have shown the misfit, but not just the model, but the difference between the model and the observations. I must have dropped a line in that code cell. Anyway, so what we can do now is we can do a grid search approach. So this code cell that's running right now, what it does is it changes the y locations of the source in steps of 200 meters. And so it steps the x location from 19 kilometers in our search space to 22.2 kilometers in steps of 200 meters. And it also changes the y location of our source from 21 kilometers on one edge to 23.2 kilometers on the other edge, also in steps of 200 meters. So we create a set of, in this case, 176 different forward model solutions, each one with a different combination of x and y center coordinates. At the same time, in this case, we leave the volume and the depth of the source the same. So we're only searching for x and y. So then in this particular cell, we will then calculate the predicted forward modeled displacement. We will mask for each one of these model runs the displacement. Then we calculate the misfit by summing up the squared differences between the observed displacement and the predicted displacement. And then we find the best fit as the one that minimizes this misfit. And so we run through 176 simulations. For each one of them, we calculate the misfit. And then at the very end, we find the best fitting Mogi source for the one that's located at x of 2.6 kilometers and y as 21.8 kilometers. So that's the best fitting source. That's the one that minimizes the misfit. Then in that next code cell, we actually plot the misfit. So we see here for each simulated easting coordinate and northern coordinate, we see what misfit we calculated. So if we put the source on one of those locations, the color here indicates what kind of misfit we get for that combination of x and y coordinates. And what you see here is that there is a progressive decrease of misfit as we get to the best solution. The best solution is marked here by this white star at these coordinates that I mentioned earlier. So that's where we have the minimum misfit between the data and the observations. You see here that this misfit function is nicely circular. What that indicates is that the x and the y coordinates of the source, they are linearly independent. So they are not correlated with each other, and we can independently estimate the northern and the easting coordinate of this source. If this misfit function would be very elongated, sort of elliptically shaped, it would indicate that there are potential correlations between the two variables that we've tried to separate. But in this case, it's a nicely independent two variables. You also see there's a color bar on the bottom. Is that blue, the best fitting misfit is not 0. So even at the best misfit, the misfit is not 0. So we can visualize this misfit at the very end. So this next code cell down here visualizes the misfit. So it first visualizes the measured displacement. So this is the observed displacement from interferometry. Below that, we visualize the modeled displacement. You can see that they're very similar. They are sort of in the same place and at the same magnitude. This middle block shows you the only the pixels where we have valid observations. If you would look at all pixels, this is what the forward model would look like. And you see a little bit better how many fringes of model displacement we would expect. And then this next code cell down here looks at the residuals or at the misfit. So what you see here is that after we subtract the best fitting model, the phase image is not flat, it's not zero. There's some residual information that's left in that interferogram. You see sort of this orangey circle here. I'm not sure if you can type, you cannot type in chat. Can you type in chat?
No.
Nobody can. So I have to tell you, or maybe somebody can speak up. What do you think this orange little halo, what might be the cause of that residual phase that we are seeing here? Does anybody have any thoughts? If so, you can unmute and try to speak up.
This could be topography.
It could be residual topography. This isn't an area where there's topographic elevation. It is related to the topography in this case. It's actually a tropospheric delay, so atmospheric delay in this case. And so later in this class, we'll talk about atmospheric delay as one of the limitations of InSAR for surface displacement. And so here we're seeing topography-related atmospheric delay in this particular case. Other signals that you see here is down here, you see a little wedge. This is a phase unwrapping error. We have a 2 pi phase error in this particular case. And then in the caldera, you see blue and red symbols. Actually, we masked out a little patch in the caldera because there's a deforming lava flow, a cooling lava flow, and I didn't do a good enough job cutting that lava flow out. There's some residual signals here. So we don't typically expect the residual signal to be all the way zero after we removed the best fitting model. Distractions can be, atmospheric delays, phase unwrapping issues, and there could also be other things happening here. There could be a landslide associated with the volcanic activity, cooling lava flows, and other things going on. So I kind of gave this away already, but you can contemplate what other signals might be in there. And so this example down here from Hawaii shows you that atmospheric delay can sometimes mimic topography. And again, this is going to come up a little bit later in the class when we talk about atmospheric error sources. So this is sort of what this notebook does. There is a homework included in that notebook that will make you do a little bit of coding, sort of guided coding if you want. And so what I want you to do tonight in your own time is you take this function, which is the original grid search function. This original function was designed to search for X and Y coordinates. What I want you to do is I want you to turn this function around and now take your estimated X and Y coordinates as known and try to search for the best fitting volume change and depth of the source. So you have to reshape this particular code cell to search for XZ and volume change instead of for X and Y. And there are some tricks that you have to look for. You see that you have to search in grid search. You always have to open up sort of a domain across which you want to search. So for X, we started at coordinate 19 kilometers and went to 22.2. It is worth keeping that search space symmetric around what you think the best fitting source might be like. And so here we already know that the volume change and the depth that we set previously is pretty close. So I would span up a search space that brackets about evenly this volume number in a search space that brackets about evenly this source depth number. And so reformulate that equation to get your best fitting variables for depth and volume change. I also want you to show me the misfit function. So there's a code cell down here where I want you to give me the best fitting misfit function. For that, I would take and modify the previous misfit function code cell. So you can just copy that code in that code cell, and you can scroll down to the end of the notebook and then create a new code cell by clicking on this plus, and then modify this code cell to visualize the new misfit function that you've created. So that's a homework assignment for you to do. There is a Moodle question associated to this homework where I ask you to provide your best fitting model solutions for the source depth and the volume change within some error. So I allow for some variation in your responses to still give you a correct answer. So go through that exercise and try that later on to see if you can model the depth and the volume change of the best fitting MOGI source for this particular event. Before I hand it over to quick questions, one more reason why this residual may not be zero is related to something that Gareth mentioned earlier today. The MOGI forward model is a very simplified model, and it makes a number of very bold assumptions. It assumes that the source is spherical. It assumes that the source depth is large compared to the radius of the source. And it basically assumes that in between the source and the surface, all of the country rock has very similar physical properties. So the way pressure is being propagated up from the source to the surface, we assume the surface in between is homogeneous between the source and the surface. So a lot of bold assumptions. And so some of the residuals could also be related to just the model not being a particularly good fit to the actual data. And a more complicated model may suit the data sets better. In this case, actually, the MOGI model works pretty well. But for other sites in other cases, MOGI may not be the best way of modeling your event. And with that, I stop here and see if there are any additional questions. So the goal was to get you into a mindset of connecting geodesy and geophysics. We'll be doing modeling actually several times throughout this class. Gareth is going to do a really nice exercise of doing more complicated modeling for an earthquake fault using an Ocado model. And you all get to model that fault and provide your personal solution. And I think there's going to be a little bit of a competition for who gets the best solution.
A competition that has no prize.
Pride, glory. We should at some point do like a DoorDash-y thing with like the winner gets like a free burger or something. Maybe in the future. Are there any questions? If that's not the case, I think the next we have a break.
Yeah.
Do we have time for a break?
We definitely have time for a break.
And then Ann Chen is going to talk to you about SAR and InSAR theory.
I'm ready when the break is over.
I think 12:20.
Melissa, do you have like a little stopwatchy thing?
I do. That would be like, what, 10 minutes?
Yes.
Yeah, let's do 10 minutes. So get up and get coffee or tea, whatever your favorite hot beverage is. And we see you shortly. And in the meantime, we'll answer your residual questions.
The setup that you're trying to model before you actually start running the model So if you saw like a very broad uplift pattern and then a very sort of focused subsidence pattern or something like that, and they were both kind of circular, you might assume that the big one, the broad one, was a deeper source that was inflating, and the shallower source was the other source was a shallower one that was deflating. Like, and then you try the sort of thing that Franz is trying to get you to do on this exercise, which is trying different source depths and different volume changes until you get, you know, a fit to both of them. Something like that. Anyway, it's 12:20 and Anne is here. So I think we should let her take it away and tell us about InSAR theory.
All right, I'll get started. And so this InSAR series session will mostly cover what InSAR measure and what is sensitive to. And there is towards the end, there will be a little bit of discussion on errors, and that will be further expanded on Wednesday's lecture. So I want to acknowledge that this lecture was developed based on notes from Paul Rosen and Scott Hensley. So those Jupyter notebook are available. So before I start my lecture, I would like to first share the Jupyter notebook that was developed by Paul and Scott. So this InSAR Jupyter notebook on the theory, and also there's some more about the decorrelation, and that there's a separate Jupyter notebook. And so my lecture slide is based on that, so they basically covers the same thing. An important note, the reason I want to bring this up is that this was developed a few years ago, and it only can be properly run in Jupyter Notebook 6, but not on Jupyter Notebook 7. So in order to do so, once you open the Jupyter Notebook in the OpenScienceLab, you have to click here, opening Jupyter Notebook Classic. And given that, then all the figures you will be able to run and visualize all the figures correctly. So this Jupyter Notebook doesn't have any code. It is really just a theory notebook. And also the homework for the session is to read through the Jupyter Notebook, and embedded there are a few multiple choice questions to test whether you understand the theory, and the answer is embedded there, so in the notebook as well. And if you have any questions after you run this notebook, you can I will be at tomorrow morning's office hours, so I'm happy to further answer your questions then. And also, well, I cannot actively monitoring the Q&A when I was giving the lecture. Other instructors may be able to resolve some of the question, and after my lecture, I will take a look at the Q&A and answer some of the question that comes up. So I'm gonna start to share my lecture slide that based on Paul's lecture. Get started. So I would like to first start the lecture, talk about the imaging geometry of a synthetic aperture radar, or what we call the SAR. So at the time, T1, a satellite or maybe a UAV that carries a radar fly over the area of interest, and it will look sideways and send out pulses periodically along what we call the line of sight direction. It will illuminate, because it's looking sideways. If you think about like having a flashlight looking, pointing sideways, it will illuminate spots on the ground. And this width is typically tens to hundreds of kilometers. So at each of the ground pixel, this is what we talk, each of the pixel is roughly about like 5 by 10, 20 meter. That's the Sentinel-1 images. So each of those pixels, you will receive two piece of information. The first information is the amplitude information. That is the amount of energy that is scattered back from the ground pixel. And the second information is the phase information. So because in the radar wave mostly interact with a scatter that is comparable size of its wavelength. So for microwave centimeter of wavelength, within each of the pixels, there are many scatters, and each of them will return an echo. And the wave is the sum of all these scatters echo. And because those scatters on the surface are distributed randomly, so that's why for a long time, if you just look at the phase information of a synthetic aperture radar, it looks just random. That reflects the fact that the scatters on the ground, those centimeter level scatters on the ground, are random. And also, and that's why when we have synthetic aperture radar, those are high resolution, meter level resolution radar imageries, people look at the amplitude information, which looks like a grayscale image that on its own is very useful for detecting surface change, like the change of the glacier, grounding lines and things like that, and also monitoring the urban expansion, and also track large movement of some surface locations. And another thing I would like to point out in this geometry is this line of sight direction. And earlier there is a question about what's the InSAR phase, how is it defined? So it turns out it doesn't matter because there are two ways. One way is to define the line of sight direction as from the satellite to the ground. And in this case, if you have subsidence and it's moving away from the radar, and that's positive line of sight. But if you adopt another definition that the line of sight deformation is defined as from the ground pixel to satellite, and then your phase would be revised. So it doesn't matter about the definition. And when you start with a radar processor, you want to check the definition and then stick with it. And after, regardless whether the line of sight is derived from the satellite to ground or vice versa, as long as you're consistent after you decompose the vertical and eastward deformation, they should be the same under different definition. So the InSAR geometry beyond the SAR is that you could imagine there is another piece of data that was acquired at a slightly different satellite geometry, perhaps at a different time T2, or maybe even at the same time T1, right? And again, from the same ground pixel A, you get two pieces of information, the amplitude information A2 and phase information phi2. So the interesting thing here is that if the ground surface scatter remains stable, there's not a lot of surface disturbance. And if we are using the phase difference phi1 minus phi2, and suddenly you start to see this very coherent, pretty fringes that looks like some kind of data. And this is about this lecture is how are we gonna interpret that. So the short takeaway that what this phase difference represent to is that the phase difference of phi1 minus phi2 can be used to infer the range difference R1, that is this range, and the range at the T2 is R2, R1 minus R2. And depending on the SAR acquisition geometry, there are two configurations. So in the first configuration, so this is mostly, this two configuration was mostly talked about in like a topography mapping. So you have one antenna that transmit, in this case, from here, and then the return echo was received at a slightly different location as this row 2 and row 1. And in this case, the phase difference corresponds to the range difference of one-way travel. And in this case, we can expand that and find each of the phase difference that correspond to 2 pi correspond to a range difference of a whole radar wavelength, that's lambda. And in the second acquisition time is like a geometry. You have each has two separate antennas that transmit and receive its own echoes. And in this way, there is a two-way radar travel. So instead of having 2 pi here in this phase difference, how you're going to relate to the range, you have a factor of 2, so that's 4 pi. And so for the topography mapping, either of these two can happen. And that's why they separate these two. But for the deformation mapping, usually we go with the second one because the radar gonna fly back at a different time. And so that's gonna be a different transmitter and receive. And so, so that's the two arrangement here. And so before we move to the deformation, the very first thing we would like to go through is that how are we going to use this phase difference to infer the range difference between the two acquisition, and also use that to infer the topography. Although right now, most of the open available satellite mission, for example, Sentinel-1 and ALOS-2 and NISAR was designed for mapping deformation. InSAR was actually when they were first developed in 80s, the primary goal was trying to map topography. And the way they kind of, although the formula works differently, but there are some common theme in between. So let's go through how InSAR can be used to map surface topography. And in this kind of setup, there is one key difference. For topography mapping, you would like this two radar antenna acquire data at the same time. Because later we are going to see that for deformation mapping, there are many different error sources. And if you can acquire the data at the same time, for example, tropospheric noise and a surface decorrelation due to the surface scatter change, and these things essentially get eliminated, and that allows a better topography mapping. So if we have the two radar antennas that fly over the same area at the same time, and then they each of them acquired a SAR image, and then you could calculate the phase difference between these two SAR image. So that's the way the topography mapping works. So for a given ground pixel of interest, P here, and we can actually write what we have known as three essential equations. So the very first equation, this delta rho, is the range difference between these two radar acquisition for the same ground pixel. It's essentially our InSAR phase measurement, the delta phi. And in this case, the P here, depending on whether you have the ping pong or classic acquisition, will equals either 1 or 2. And the second equation is related with this satellite geometry with this triangle A1, A2, and a P here, right? And so you can see this B is the distance between the two satellites. That is what we call the baseline of this imaging geometry B. And this rho is the range between the satellite at A1 and the ground pixel P. And this rho plus delta rho is at A1 to A2 to P. So all of these numbers we actually know, so we can write them up based on the law of cosine. So this is a B squared plus rho squared minus rho plus delta rho squared divided by 2 rho B. That's here. And the cosine of the theta here, alpha plus this theta here is a 90-degree minus theta. So that's this one. And then based on the trig identity, you switch that cosine of that angle A2, A1 to P to this sine inside is theta minus alpha here. So everything within this second equation tells you the geometry constraint of this particular imaging acquisition. And the third one contains what we're interested in. So this H here is the height of the satellite at A1, what we know, given that we know the orbital information. And this Z is the topographic height of that ground pixel Z. That's what we're interested in. And again, rho is what we can measure from the radar. And so when you're sending out a pulse from the satellite, at every pixel at a later time, you receive the return from a particular ground pixel. That time delay can be used to infer this rho here. And then again, this theta here is the radar look angle. That's again what we know. So it's three equations. And the only thing that we don't know is Z. So one can imagine if we go through the algebra here and we can solve for the Z. So to derive how to link what we are measuring, that's a delta phi here, to Z. And the derivation was discussed in more detail in the Jupyter Notebook, but one of the approximation that can make the overall derivation a little easier is to adopt this so-called parallel ray approximation. So essentially assume because the radar satellite is very far away from the ground pixel, this line here and this particular line here is parallel. And that's what we mentioned, like this two radar has to be pretty close to each other so that the line of sight direct angle does not really change much between these two SAR acquisition. And in this case, the parallel ray approximation can be used, which basically say the delta rho here will be simplified as the B times the sine of the C minus alpha here. Later on in the full paper, there was actually derivation. It doesn't matter whether you adopt this assumption or not, the eventual derivation, the result would be comparable, which means this approximation, when you look backward, is actually a reasonably good approximation in this case. So I'm not gonna go over the whole derivation here, but what I want to remind people is if you just use some kind of a physics intuition, so as you're moving at a different ground points here, right? And so what we're measuring here, the delta, the phase difference between the two SAR acquisition is sensitive to this delta rho here. And what actually gonna be able to make the delta rho change, given this is the same time, so there's no deformation, right? So there's actually two key components. The first component is that assume there is no topographic height variation. It's just a very flat Earth, right? And when you are moving from ground pixel from a near range location, as you move further away, and you can start to draw different triangles, but you can see this delta rho would change. So even there's no topography change, there is a phase change just simply as we move from the near range to far range. And that is what we call flat Earth fringes. So if you form an interferogram without remove anything, you will see this very large ramp from the near range to far ramp that is related with the simple fact that as you move from near range to far range, this delta rho will change over distance. And then we can actually calculate what this flat Earth fringe looks like and then remove that. And after that, what we're gonna find is that the remaining phase, that what we call a phi topo, is related with the elevation difference. That's a delta Z between two locations on the Earth's surface. The whole derivation is long, but the interesting here is in this particular relationship, this is our final result. So you can see this is the amount of InSAR phase you can measure at two different pixel location after you remove the flat Earth fringe. And this is the elevation difference, that's dz at these two locations. So they can be related with a fairly long, complex number. But if you look into what's in this, so 2 pi, p is either 1 or 2, depending on the imaging geometry. B is the baseline, and then lambda is what we know the radar wavelength. Rho is the range at that given location, which is known. So everything here, and then theta and alpha related with the imaging geometry. Also, once you know the satellite orbital information, you know everything in this this one, so you could actually reduce that into a single coefficient that leads to a linear relationship between dz to phi topo. Right, and that is why after you remove the flat Earth fringes, when you're seeing the remaining topographic phase, it will looks like these contour intervals, those fringes that hugs over the volcano, and every time you're counting a phase cycle, and that will be translated based on the number here into an elevation difference. And this is how we actually use InSAR phase measurement in this setup to infer the topography of the area. And of course, in this location, one thing we could control here is this B, that's based on how far away these two satellite is apart, right, this B. And so for the topography mapping, you would like to have a relatively large B, although there's a limitation on how large it can be. And later we are going to talk about the critical baseline. So within a reasonable range, usually for topography mapping, you would like to have a relatively large B because that means for a small elevation change, you would lead to a large phase variation. That means the phase will be more sensitive to the topography phase, right? And so that's for the topography mapping. And so how are we going to actually implement that? So there are two different setups, and both were actually in operational mission in the past. So the very first one is the setup for shuttle radar topography mission, where you have a shuttle that has a radar that on board the main shuttle. And then there is, in order to have a two receiver, that is acquiring data at a slightly different location. So there is a rod here that is about 60 meters apart. And so you have a receiver here and a receiver right here, right? And so usually, ideally, you would like this baseline to be long, but when it's too long, it's probably kind of hard to fly in this way. So that's the kind of what they set it up for. So this SRTM data was launched in 2025 years ago. And so far, it is still one of the more commonly used topography data set that we use. And we want to mention that radar data has a very good advantage of a broader spatial coverage. As we mentioned earlier, each single flight path, you can illuminate an area of tens to hundreds of kilometers, which means you don't need a lot of repeat to cover the entire globe. So SRTM data, I think the actual data acquisition is only about a little over 10 days. But of course, the post-processing takes a little bit of a longer time. So a more advanced setup was launched called the Tandem X. It is still in orbit, but right now it is not openly available. So it might be available in some area, but unlike the SRTM, everyone can download it. There is no public hub for you to download the data. So the change here is that there's two satellites that fly in formation. So acquiring the data of the same area at the same time. And it's because there are two satellites. And so you could make them a little bit further apart to be in the ideal baseline of hundreds of meters. And so because a little bit larger baseline, the SRTM, the Tandem XDEM has a better accuracy in the retrieved DEM data product. So briefly, I would like to compare three technologies for generating the global topography map, which is a very important data set for many different uses. The very first one is to use many optical images over the same area that is acquired at a different viewing geometry. As you know, when you're looking at different images, they are going to appear stretched depending on where you're looking at it. And when you know where the position where those images were taken, and then you could combine them and constrain a depth image, and that is the topography information. And similarly, you could actually, if you have those radar amplitude image over diverse viewing geometry, you could technically perform stereo imaging for radar images as well. So the second techniques, usually you do the laser altimeter. So what you do is you have this laser altimeter fly over the area. You shoot a laser down to the earth, directly downward, and then you basically using the time delay to, and also where your instrument is to calculate the topographic height. The advantage is that those LiDAR measurements are very, very accurate, but usually they suffer from poor spatial coverage because when they fly for a single path, you can think about instead of an image for a single path, you get a profile, 1D profile along the radar path since it looks directly downwards at a point. And so, that's why for laser or like altimeter topography mapping, typically you're interested in either a regional area where you would like to have like be able to survey with very dense sampling, or maybe over a larger region where the topography kind of a very, very slowly, so that you don't need to have a very dense sample to get an idea about the overall topography structure, for example, the interior of the ice sheet. So the third one is radar interferometry. And so compared to the optical sensor, I think one of the clear advantage for using radar for mapping topography is that it will penetrating through cloud. And that means in area where you have 90% of time cloud coverage, the radar interferometry is typically a ideal like technology to acquire topography. Of course, all these three methods are used and combined usually. So I kind of, since it comes up, I thought it's good to bring this up. Assume, given now we have a good topography map, and assume we have the radar satellite that are coming back, a single radar satellite that is coming back in a frozen orbit at a different time. And in this case, S1 and S2 would be maybe the same satellite or a different satellite, but flying back at the same area in a different time. And if the radar, the ground pixel also moved from A to A prime along the radar line of sight direction. So if it is moving perpendicular to the line of sight direction, it's not going to be sensitive to that. But if it is moved along the radar line of sight direction to A prime, then this delta D will also lead to a range difference between these two SAR acquisition. So in this particular case, the InSAR, the radar phase measurement difference between the two SAR acquisition will have a topographic component and also a deformation component. And since we already know the topography, perhaps from the SRTM or TandemX mission, and we also know the satellite geometry, so we know where S1 is and S2 is, we could actually calculate the expected topography phase based on the known DEM. And that is why when you're processing InSAR data for deformation mapping, DEM is a required data because you will need that to remove this topographic phase. And after you do that, then usually what we call that a flat interferogram means the topographic phase is removed. So this phi1, phi2 minus phi1 minus phi topo will be proportional to the deformation, line of sight deformation, delta D. That's when this pixel moved from A to A prime. And here is our second relationship. Earlier we mentioned for the topography mapping, you could connect the InSAR phase difference to the topographic height change through a factor that you could compute based on satellite geometry, right? And here we have our second linear relationship. That is, after you remove the topography phase, this residual phase is proportional to the line of sight deformation with a 4 pi divided by lambda. In this case, you always count for two-way travel. So deformation mapping, there is no p, that factor here is always p equals 2 cases. And given these two factors, right, so these are just that factor that is in this two linear relationship. And we can actually see a very interesting note here is that using InSAR, you can measure, it's usually, I'd say, what is InSAR? It is a technique for mapping surface topography and surface deformation. However, the same techniques, when you're trying to derive topography or deformation, their sensitivity is quite different. So for a small phase change, if you want to translate it into the topographic height change and the a linear factor is written here, right? And then you can plug in common baseline, usually hundreds of meters, and a common look angle about 30 degree-ish. And so what you will find is that the sensitivity is at a meter level. So it's typically less accurate than the LiDAR measurement. So it's a few meter, and I believe SRTM is about 10 meter accuracy for topography mapping. And but once you remove the topography mapping, right, and so the residual phase, when you're talking about a small deformation, and so the factor here is 4 pi divided by lambda. And this lambda, depending on the radar wavelengths, so for C-band, it is 5.6 centimeter for Sentinel. X-band is typically we're talking about 3 centimeter. L-band is 24 centimeter. And that is why when we're talking about InSAR for displacement mapping, and so you can usually achieve centimeter level to millimeter level accuracy. And that is another reason even SRTM data is old, it's 25 years old, it's not perfect, right? And so there's likely errors due to the topography change that within this time. But you have to have a really, really big change in order to make an impact to the actual deformation mapping accuracy. So when you remove the topography phase, their sensitivity is quite different. And once we have this phase fringes, so typically here is an example of what the interferogram looks like for coseismic deformation. So radar data are complex numbers, so the phase is the wrapped phase is part of that complex number, what we're interested in. And so the phase here, you can see from each of the color cycle from green to another green is a cycle of 2 pi. Similarly, for red to pink is our cycle of 2 pi. So ideally, you would like to have this actual phase measurement from far away and continually moving, and so that we can actually convert that to line of sight deformation by divided by 4 pi and times the lambda, right? And so to change that, but because the radar, those phase were wrapped phase, which means it only record phase in this circular kind of range. So once it's reached 2 pi, it will start over from minus pi to 2 pi again. So the phase unwrapping, which you could do by hand, I believe we have maybe an exercise at some point on that, is that you can start by tracking the phase. And once you detect a jump, you just add 2 pi to this whole region here so that it come back into a continuous phase. And of course, the third part, and you need to add 4 pi, right? And so the phase unwrapping, if you made an error, and then usually it is a integer cycle of 2 pi. And if you don't make an error, so hopefully after unwrapping, you will see smoothly varying deformation field from the wrapped phase. And by looking at it visually, so this is 1D idea. So the phase unwrapping for InSAR need to be done in the 2D form. So on the left here is the wrapped phase with many cycles. And for this particular case, you could just starting from a far field, like counting from InSAR measures a relatively phase difference. So you start from a far field and basically count 1, 2, 3, 4, 5, 6, right? 6 cycles. And then that's kind of unwrapping by eyeballs. But luckily, we have a good software that will be able to perform the 2D phase unwrapping for you. So here is after unwrapped, you could start to plot the continuous phase and then convert it to the line of sight displacement by the factor of 4 pi divided by lambda. And we will also start to talk a little bit more about the error sources here. Here, I just want to give a brief kind of introduction of the error sources. And on Wednesday, we're going to have a longer series session on how to mitigate some of the main error sources. That's kind of this is a great technology, but I often want to remind people, well, this particular term is what we're interested in. So this is assumed for topography deformation. Delta phi is the flat Earth interferogram. Can be related with deformation of the to SAR position time, but there are also many error terms. So the very first one is actually the error due to the DEM, as we mentioned. In order to for the deformation mapping, you need to have a topography data set to calculate the expected topography phase and remove that, right? And if you made a mistake, then you would have a small error here. And then the second term is the tropospheric noise, and then third term is ionospheric noise. I'm gonna give an example what it looks like, and for the specific characteristic, on Wednesday we have a session on that, and also we have orbital error and the decorrelation error and unwrapping error. These two are usually related. If you have a very coherent little decorrelation, the unwrapping typically can be done very easily, and there won't be many errors associated with that. But for the area where you start to have severe decorrelation, and I will give you a couple examples about what the decorrelation looks like. And then usually you will have a lot of the unwrapping. What you will notice is going to take a long time, and also the result won't be reliable. And because each time you made an unwrapping error, it is at least 2 pi times n, where n is any arbitrary integer number. So it's a fairly large number. So once the unwrapping errors start to show up, then it usually will dominate in your final solution. So that's kind of all these source terms. So let's just take a look at each of them. So the very first one, I tend to find that this one is a little bit easier to deal with, is what we call an orbital error. And so as you can see here on the left is an L-band ALOS data over an groundwater aquifer in San Luis Valley. And so what we can see here is that there is a rainbow-like linear ramp, right, from this corner to this corner. And this is fairly large because this is an L-band center. So you can see from blue, you move to yellow to pink to blue again. So that blue to blue is a whole phase cycle. So if you're interpreting that all as deformation, that would be half of the wavelength. So L-band 24 centimeter would be correlates to a 12 centimeter of deformation. And of course, based on some of the prior knowledge, that seemed to be too big. And also for agriculture, for groundwater aquifer, you kind of expect the deformation occur above the ground aquifer, follows some of the aquifer geologic set map, right? And so where the aquifer are, rather than just a plain ramp. And if you look at the data acquired over this area, at many interferogram, you will see this kind of ramp in different orientation, sometimes worse than this. So these kind of phase ramp are likely to due to orbital error, but of course there are other common cases, like sometimes the ionospheric noise gonna give you a ramp-like signature, or some of the larger tropospheric noise. There's a larger scale, long wavelength tropospheric noise sometimes will also looks like a ramp. And for this particular case, I know this is orbital error. It's because I have data that are quite from other sensor, and it just doesn't show this kind of ramp. So it's kind of very mission related. So where the orbital ramp is, like if you start at a location, as you move further away, if your orbital information is not accurate, it starts to diverge from the true orbit, and then you start to see a ramp. And how are we going to remove that? And simply you could take this as your unknown and fit to a 2D linear solution and remove that. And after you remove that, you start to see this very light yellow color. So these are actually later on This is after I have done this, done some of the validation over this area. So this light yellow color was actually the uplift due to the aquifer recharge. And as you can see, these kind of a small deformation signal, maybe a centimeter or two, can be only visible after you remove this kind of a larger scale ramp. So, another thing I would like to mention is that how do you deal with this type of error? And so usually after you process the data, you notice this kind of ramp in different data set. And usually you could just try to remove the ramp and then do the analysis. But also you have to kind of take into account some of the prior knowledge. I have in one case, your deformation signal itself looks like a ramp-like structure. And in that case, if you remove a ramp, then you will also remove the signal as well. So as a common standard for my own group, so usually I derive two sets of solutions, one with ramp removal, one without ramp removal. And hopefully we have some other information, perhaps with GPS or some in situ knowledge about what the signal you're looking for to decide which version of the data give you a better quality result. And the second error is from the DEM error. And so how do you know there are DEM errors? So typically this type of error gonna be more noticeable in area where you have steep topography. And then also the way to identify some of the artifact from DEM error is that if you have maybe two different source of DEM, one from SRTM, maybe one from some other source you get, and you are processing the same set of data, and everything else is the same. You're just switching from a different version of DEM. Somehow your topography removed, the flat interferogram looks different. And that's definitely related with the DEM topographic removal, right? And so in this case, you can see this one has a lot more noise, and that typically means probably likely due to DEM error over a region. So what I have found is SRTM data. And another idea is even for the same port DEM, if you start to see some of the artifacts that start to be more noticeable in interferogram with longer baseline. I remember when we were doing the topography mapping, the same delta Z will lead to large phase variance. So when you have a longer baseline, right? So the DEM error will be proportional to that. So for deformation mapping, if you want to limit the impact of your DEM, then actually a shorter spatial baseline is preferred, so that most of the phase difference is due to the deformation that is not baseline dependent, right? But the topographic phase is DEM dependent. So that's another way. If you start to see artifact gets worse in interferogram with larger baseline in the same location, and kind of the same artifact just looks like a lot worse. And that's usually also related with DEM. And so for DEM type of data, what I have found is Sentinel-1 there has very good orbital control, so the baseline becoming small. So I start to notice less of those kind of artifact. And also if you have a DEM, so what InSAR is really sensitive to is the relative error within your DEM. So if your SRTM data, they have 10 meter absolute error, right? But the data quality is uniform, and so the relative error between pixels is fairly small. And that's usually is good enough. But if you have some like a very high resolution data acquired from multiple group, and then you merge them together, and each of them may be calibrated differently to a slightly different datum or something like that. And so the interferogram generation is sensitive to this kind of a relatively error. And sometimes you could even see, oh, that's a small patch of the data probably generated by a different source, because you see a sharp boundary in between. So that's kind of the idea. So usually, so in my experience, for the mid-latitude and equator area where SRTM data available, they're usually good enough if you don't have too steep of a terrain. And for the Arctic region, the Arctic DEM have been using that, has usually give a pretty good quality of interferogram. And the third one is the ionospheric artifact. So I will talk more about that. But the key idea here is ionophoric artifact will depending on your wavelength. So longer wavelengths, you're more prone to large ionophoric artifacts. So if you're working with X-band, you usually hardly notice anything because of the relationship is inverse proportional to the frequency of square. So that means L-band like nice are going to be very like it's going to be an issue. And also the ionosphere artifact tends to be worse in equator region and the Arctic region, and generally milder in the mid-latitude region. And also, of course, it's related with the solar cycle. So I believe around 2010, that's like in the relatively low solar activity period. And even for L band, what I find is you can see some ionosphere artifact here and there, but usually I can deal with that by throwing these two away, and the majority of them gonna be good. But that won't be the case when it is L band and also an active solar year that is coming. So we're gonna talk more about how to mitigate that on Wednesday. And then one of the quick notice is that the ionophoric artifacts sometimes it's gonna have because of the radar data looking sideways. So the range direction where it's like a near range is close to the radar, far range is away from radar, and the azimuth direction is where the satellite is flying the direction. Right, so it's different. So for the ionophoric artifact, it's usually have this distinct pattern that has a larger variation as you go through azimuth. So you can see these kind of fringes right here. Those are the ionophoric artifacts. And there's a little bit of a decorrelation here. That is also the ionophoric artifacts. The idea is that when you have those tech changes along the flight path, and it can lead to the pixel location shift in the azimuth direction. And so here you can see there's a positive shift and a negative shift. So due to this ionophoric anomaly. So when the pixel shift is above a pixel, and then this leads to usually decorrelation. But if it's within a pixel, then you see kind of an additional phase pattern. So although it looks different on this image, but these and these decorrelated region, they are all from the ionophoric anomalies. But luckily, there are ways to mitigate that. So we will talk about that more on Wednesday. So another dominant factor is tropospheric noise. And in fact, a lot of those techniques, like time series techniques, was mainly trying to mitigate that. And it was introduced by the variation of the pressure, temperature, and water vapor in the troposphere. The issue for tropospheric noise is that it's everywhere. No matter where you're studying, there are going to be some level of tropospheric artifacts. And also it affects all radar wavelengths in the same way. So earlier, sometimes you might hear people say, well, X-band has a shorter wavelength, so it's more sensitive to smaller deformation, right? And because each of the phase cycle would only correspond to 1.55 centimeter of deformation for X-band. But that didn't consider the fact that that one small deformation would be present in the same amount of tropospheric noise that is wavelength independent. So no matter what wavelength you're using, you have to deal with the noise, which can be as large as tens of centimeter. Like earlier, my slide was saying up to 15 centimeter, but as you're moving to a larger region, sometimes it can be even go beyond that. So if you have a centimeter level deformation signal and there's tropospheric noises 10 times more, you definitely want to take that into consideration rather than just say, well, I'm going to use X-band and then it will resolve the issue. And these noise going to be there, present there for your site. And kind of site dependent, usually what is worse, would be like a tropical area with high topography variation, humid area. So that's the area that's the tropospheric noise tend to be be worse. And so they got usually two components. One is correlates with topography. As you can see, if you have topography, the amount of the range is different, right? And so of course the amount of tropospheric delay you see along the path would be different. So usually that's what we call a stratified component. But more importantly, it also contains a component that is what we call a turbulence noise. That is can be considered random in time. So for the stratified component, and we will talk more on Wednesday, that you can typically predict that based on a weather model, which gives you some prediction of the pressure and water vapor temperature, and then based on the topography model, you could actually predict the stratified component with a reasonably good success. But those turbulence noise, it's just there's a random cloud here versus there's no cloud at another time. These kind of rapidly changing, very localized topographic feature. And these are typically not be able to captured by the weather model. And so that's the part that I usually stuck with, and so we usually want to mitigate that through some kind of a time series inversion scheme, perhaps using a temporal filter, given that it's random in time, or maybe incorporate a deformation model and to separate the signal and the noise. And one of the last, but perhaps I think one of the most important one is decorrelation. And before I introduce the concept of a decorrelation, I want to kind of go back to kind of talk about what is decorrelation. As you recall at the very beginning, if you look at the phase measurement of a single SAR image, right? And so the phase would look like just some random phase you randomly draw from 0 to 2 pi. And this is the case when the correlation equals 0. There's no correlation, there's no spatially coherent signal, right? And if the surface scatter doesn't change much, and then your phase difference between these two acquisitions can be used to measure the range difference between the two times. And in this case, you start to see this spatially coherent phase. So this is what we call a high coherence. And you can see in this bottom region, in this particular example, there are some phase noise. So this is some moderate level of decorrelation, but perhaps not severe enough to mess up the phase unwrapping, right? And so this is completely decorrelated, zero correlation. This is very high coherence, close to 1, and this is probably somewhere like in between. And usually you don't have to worry about decorrelation in this kind of a case, perhaps start to be a little concerned in this case. And when the decorrelation is severe, close to 0, and then these are not pixels that contain valuable information, you have to exclude those measurements in your deformation interpolation. And how are we going to be able to actually evaluate the coherence? So there are many different ways. So the very first way, when you are running ICE, they are going to give you something called a correlation of it, and it's matched to each individual interferogram. And so it's the same size. So at every pixel location, you have a number between 0 to 1, where 0 means it's a very low correlation. 1 means that it's a completely there's no decorrelation at all. It's a data-driven approach. So the formulation is long. ICE will automatically calculate it for you. But essentially what that equation does is it is a similarity measure. So consider you have a location of interest here. They just draw a small box here. And basically that number between 0 to 1 basically just is a similarity measure to tell you how similar within that small box the phase are. So if they're in this green area, everything has the same phase, you get a very high coherence. And in this area, there are some variations, so you get something maybe 0.5. And in this area, it's completely random. They're not similar at all, so you get a similarity measure of 0. So this is something it is calculated for you as a very rough way to tell you how good your phase are. So high correlation usually leads to very easy unwrapping, very small unwrapping error, low correlation, unreliable unwrapping, and basically there's not a lot of useful information in this. But I do want to mention that this correlation measure driven from a data-driven approach is not, it's like, it's always, you can look at it, but sometimes it's not super reliable. So in this particular case, it should be 0. And if you plug in the correlation, you will get something non-zero. So there is a little bit of bias in this measurement. And also depending on different software you use, so the absolute number may change a little bit. So typically what I recommend you to do is you generate an interferogram, and then you could maybe experiment a different threshold based on the correlation matrix you get. And then, of course, when you use a lower threshold, the more interferogram pixel would be count as a good coherence, like above the threshold, right? And then you can see the amount of pixel you selected, and then based on the phase quality, you actually match. So don't just use a fixed threshold of 0.5. So that number doesn't mean anything depending on your area or different software. But what I find is typically you're trying to tweak the threshold and see if it can give you a clean cut of good measurement versus a bad measurement. And here is an example, and then we can see it's the correlation map in the same area over 2 interferogram. One is 1 day apart, which usually means it doesn't have much decorrelation, right? And then one is 6 months apart. And there are several takeaways here. Is that the very first one is that usually the phase tends to decorrelate over time. So the longer you wait, the more likely the surface change. Some of the common strike, like for example, agriculture field, and after 6 months, the small plants have grown to bigger plants. That will decorrelate your phase because of the surface scattering of those scatters has changed, and that violates the assumption of InSAR between the 2 SAR acquisitions. The surface of the scattering surface should remain relatively unchanged. And so that's why, and another thing you can see is even for the same temporal baseline, the decorrelation rate at a different pixel are different. So usually you can maintain very good correlation in area like a city, urban area where you have a concrete surface, unless they redid the road surface, right? Or they dig a hole there, that will definitely decorrelate the phase. But otherwise, if it is just an urban environment with buildings that is stay there with minimum change, they can maintain coherence versus a long time. And another thing is that usually bare rock, like volcanic rock that doesn't have a lot of vegetation, will usually maintain coherent over time. So the agricultural field, on the other hand, that people work on it, irrigate, and harvest and plant new stuff all the time. So these are area tends to be, you can even see in this 1 day, even there are some drop of correlation perhaps related with some like irrigation over this area. So it tends to decorrelate relatively fast. And also in the sandy portion, because the sand can be blown away from time to time, there's no stable scattering surface. And so they tend to also decorrelate reasonably fast. So that's kind of the thing you have to keep in mind, that the decorrelation tends to be worse over time, but the rate of decorrelation is different. Typically, there's a strong correlation with the land cover. And in turn, we have a Jupyter notebook that talk about many sorts of decorrelation. And so I'm trying to keep it simple here, and we will talk more in the time theory section on how to mitigate some of these. But what I have found is most common decorrelation is temporal decorrelation, because you look at interferogram, the 3-year interferogram will be more decorrelated than the 12-day interferogram, right? And so one of the most important one is temporal decorrelation, and that's typically is going to be very noticeable in anywhere area you have a vegetation, dense vegetation that has leaves that grow and and change the scatters, right? And so the spatial decorrelation is usually going to be a concern typically because now the Sentinel, the spatial baseline is fairly small. So if you have the earlier mission, for example, ELOS, sometimes when you go to like 5,000 meter spatial baseline, you will see some level of spatial decorrelation. And so if the idea of where the spatial decorrelation is coming from is from the fact that for InSAR to work, the two radar satellite has to look at the same pixel of interest through almost identical imaging geometry. So they cannot be too far apart. And so if they're very far apart, the baseline is too long, then the scattering probably doesn't work the same way. And that will lead to a spatial decorrelation. And there is a theory about a critical baseline. So basically, if the satellite is too far away beyond that critical baseline, there's no correlation going to be maintained. And so luckily, so usually when they're designing the mission, they usually try to make the repeat cycle well below the critical baseline. So that's not something in active processing you have to worry about, because if you look at Sentinel, the baseline tend to be 10 meter to hundreds meter. So that's usually not going to lead to any issue. However, if you have an area with very steep terrain, so that can make even a pretty close together satellite looking at the surface looks like a very different incidence angle. So the spatial decorrelation can also occur in area where the surface, like the terrain is very steep. But if you're in flatter area, I don't think it tend to be an issue anymore. So the thermal decorrelation is another term. I usually don't notice that because typically the most prominent one is a temporal decorrelation. And finally, I would like to mention for the decorrelation, and it's also clearly related with the wavelengths. Typically, a longer wavelengths usually means like if your surface scatters moved a little bit, it doesn't feel like a big change to this longer wavelength sensor, right? And so L-band interferogram tend to maintain better coherence over the same area of interest. So if you're urban area, I think both X-band and L-band can work equally well, because if the surface remains stable, it doesn't matter, right? But if you're working in area with some level of moderate change due to maybe vegetation and some other cases, in this case, the L-band data has a much better chance to maintain the coherence over time. That allows you to have enough good quality data for time series analysis. So that's the end, and we will hopefully go through some of the detail in the Jupyter notebook. That is your homework. And also on Wednesday, we will, in our InSAR time series session, we will talk about some of the strategy, mostly for mitigating ionospheric noise, tropospheric noise, and the decorrelation. And a lot of these features are available through MinPy, and so hopefully by having this theory, give you some better idea about the strategy that works the best for a particular site. And that's it. Thank you.
Are there any more questions arising? We've been doing our best to answer them as Anne's been going along, but if you want Anne to answer them yourself, and this is your time. This is your time to ask.
Yeah, I will be available tomorrow at the office hour, tomorrow morning too.
Yeah, so there were a bunch of questions also on DEMs in chat, and as Anne has said, is like how accurate your DEM has to be depends a little bit on the baselines. So if you have a sensor that has short temporal baselines, you get away with a little bit more than if your baselines are fairly long. But if you think of DEMs, don't just think about their vertical accuracy, but also think of their age. Because a DEM that's 10 years old, even if it's very, very accurate, may not be a good representation of what your surface looks like today. Kilauea or say volcanoes make a lot of sense if you have topographic changes related to eruptions. They may not be captured in those DEMs. So sometimes a more recent but technically less accurate DM can actually give you better results compared to a maybe older, by numbers more accurate DM.
Yeah, now I have a comment here. If you only have one DM, just use that. But if you have a two DM, I recommend you to make interferogram using both interferogram, picking one of the longest baseline. If you don't spot any error, which means it doesn't matter. If you spot the error, then you can try to drop the baseline and see if that's still a problem, how bad it is, where that's a problem, then decide which interferogram looks better. Because if you only have one DM, that's all you can have, right? Then you might be able to fit a perpendicular baseline dependent term and remove that, or you can limit it to the small baseline for time series. But if you happen to have two DM, definitely try to make two versions and compare them.
Yeah, and Yunjun is that Friday, will show you some ways of how you can try to estimate residual DM errors if you have many, many interferograms. So we'll get to that again later. Technically, I think we have a break coming up, but I think what we should do, Melissa, are you
very
ready?
Short break.
A short break is maybe to do a group photo.
Oh yeah.
Yes. Yes. So if everybody could, that's online right now, could turn on their video so that we get your lovely face on camera.
You have to turn yours on too.
That's right.
Not one of those people that can talk and do things at the same time.
And are you taking the screenshots? Do you have a setup that's... Yep.
Yeah.
So it's several pages for me, but
It's
look
working.
at all of you guys.
If you don't have a camera, that's okay. Sometimes we don't.
You got to count down so we can all smile.
Are you going to give us a countdown, yeah, so that we smile on cue?
Waiting for a couple more people to sign in here. Go up.
Franz, you have to come back.
I can show off my model of NISAR. I could do an Eric. Wait.
There we go. Okay. In 3, 2, 1, smile. Okay. Oops. One more. And 3, 2, 1, smile. Oh. Okay. That's it for me.
All right, shall we have a very short break? Come back in 4 minutes.
4 minutes.
1:30.
I'll get some extra coffee.
Yeah, more water.
So the next exercise is going to be on a notebook again, so you can get prepared for that. We still have 2 minutes. No, 1 minute. But if you want, you can get ready for that exercise in 1.4.
Welcome back. So I'm leading the next session. I guess I should just start by sharing my web browser. Pick the right window. Here you go. How's that looking?
Good.
I'm sure he's looking lovely.
Yes. Carlos built.
So we are going into the 2025 ICE Plus 1.4 interpreting a coseismic interferogram, and this is the notebook here. Looks nice. Yeah. Okay. So if you can follow along, this is a good place to start. For this one, it doesn't really matter what the kernel is. It will work with everything, I think, because it's just for display. Okay, so what this exercise is about, and what you will see is an interferogram unwrapping and interpretation exercise. So we have an interferogram here for you to look at of an earthquake that happened in Turkey in 1995. It's a moderate magnitude earthquake. It was a 6.4. It was actually quite damaging because it occurred right next to a town of Dinar in Western Turkey. The earthquake had a surface rupture, so you could actually go into the field and see places where the ground was separated and offset by 25 to 30 centimeters. And it was one of the earlier earthquakes to be studied with ERS InSAR back then in the 1990s. So there's a bunch of files that you can see here that are provided for you, including PDF documents that contain the interferogram. Here it is. Also a PDF document of a grid to fill out. We're going to try and fill in from the interferogram which areas went up and which areas went down in the earthquake, and plot them on this profile. You'll see on the interferogram itself there is a profile line, goes from X to X prime through this interferogram here. I guess you could zoom out so you can see it all. Yeah, there it is. So one version of this exercise could be done on paper. If you actually had a color printer and you could print these two plots out on the same scale, then the grid here actually is the same size as the profile line there. But since we're all online, I don't think that is necessarily practical. But there are other things we can do. I'll show you in a minute. So yes, your job is to interpret this interferogram. And here it is again in the notebook. There's some information that I give you in the diagram, in the text and the caption here, which as a good citizen who understands that there are sign conventions, is hopefully will tell you what's going on here. So here in this case, each successive cycle of colors from blue to yellow to red indicates an increase in the distance between the ground and the satellite. In other words, a positive range change of 2.8 centimeters. That 2.8 centimeters is half of the radar wavelength of ERS, which was the satellite mission that was used to collect this data. And yes, so blue to yellow to red, and you can see blue, yellow, red, blue, yellow, red, blue, yellow, red, and so on. That indicates an increase in distance between the ground and the satellite of 2.8 centimeters. And you can see this pattern extends over quite a large area. The scale bar here says that this is 12 kilometers in length. So, for example, the surface rupture of the earthquake is indicated by this line here, and that is of the order of about 12 kilometers, maybe just slightly shorter. So that's the kind of spatial scale you're dealing with. The fringe pattern extends over tens of kilometers. Another thing that we provide you with is this white dashed line here, which for the purposes of this exercise represents zero deformation. And you can also treat both ends of the profile as if they were at zero. That would be that is helpful. And so this is in kind of green, which is halfway between blue and red. So you can treat this as zero, as I said, and then this would be half a fringe, and then you count the fringes basically and estimate how much displacement you have based on this idea that each fringe is 2.8 centimeters. At this point, maybe I might stop sharing this and show you briefly some slides that I have. that maybe on a slightly simpler case that you could use as a means of trying to understand how this unwrapping process by hand would work. So let me just share my whole screen briefly. Minimize a few things and maximize some others. Okay, so this is another similar case. This is another earthquake. This was a slightly smaller earthquake. It was a 6.0. It happened in the Nevada desert. The Wells, Nevada earthquake of 2008, measured with ENVISAT, which is a very similar radar to ERS. Same deal. That blue to yellow to red is 28 millimeters of displacement, and that's away from the satellite. So here what you would do is you would pick your zero fringe, this one. Okay, and then you count fringes inwards and go from blue to yellow to red. That's the next fringe there. And that's an interval of 28 millimeters more deformation. Then blue to yellow to red again gets you another fringe that's 56 millimeters. Blue to yellow to red again, another fringe, 84 millimeters. And at the very middle, there's a transition from red to blue again. That would indicate 112 millimeters. So these are effectively contours of the movement of the ground. This is the line of sight displacement. Most people, when interpreting this for this style of earthquake, would assume that the majority or all of the deformation that you're seeing is vertical. That is an assumption, but I mean it's a reasonable one. You can make reasonable interpretations on that basis for this type of earthquake. ERS and ENVISAT both had very steep incidence angles, so the radar was pointing at a very, very acute angle to the vertical. So it's not a bad assumption. But this is the sort of thing we would like you to do on your profile, on your interpretation of the interferogram from the Dinar earthquake. But there are more fringes and it's a bit more complex. And that's deliberate, right? You're going to see some of the complexities in these kinds of interpretations. Not every earthquake is as simple as the Wells earthquake. Okay, so while I get my stuff back together, share my other window again. That one. Okay, so there are some questions that you can answer, and I would like you to answer, like amongst yourselves, once we have gone through this exercise. There's also some terminology involved, because geologists love terminology. So this particular tectonic environment was an area where the crust is being extended, it's being stretched. And that is the type of environment when you will find faults that we typically call normal faults. Now, whoever came up with this terminology, this must have been the most common type of fault that they found, because whichever one you pick as being normal, I guess is very much a matter of like preference. But anyway, that's what we call them, and these are faults in which one block of material is faulted downwards with respect to another. So you can imagine if the crust is being stretched, one way of stretching the crust would be to rift it apart by pulling blocks away from each other a bit, and that's what goes on. And typically, the vertical part of the motion is that one block goes down, the other block goes up a bit, and you create this kind of step in the landscape over time. With repeated earthquakes on such a fault, and this is exactly what the Dinar area looks like. I could have shown you another slide or two maybe about that, but maybe we'll get back to that later. So there are terms that we use for the two sides of the fault. One block of material is above the fault. The fault has what we call a dip. It dips downwards, and so there's material above the fault and material below the fault. Right. The stuff below the fault is called the footwall of the fault, and this I think comes from mining terminology. If you mined along a fault the foot, which you often did, if you went along a coal seam, you would run into a fault. If it was a normal fault, you would expect, if it is the fault was tipping towards you, to the material to go up the fault plane. But anyway, the foot wall is the part that you stood on. If you were standing on the fault, the stuff below your feet is the foot wall, and the stuff above you is the hanging wall, because it's above your head, and you could hang your lantern on it. Okay. So there are some questions that ask you how many fringes there are on the hanging wall side of the fault, and how many fringes there are on the foot wall side of the fault, and can you figure out how those two parts moved? Okay, so hold those thoughts when we start to like interpret this profile. Do I tell you which side is which? Yes, I tell you that the hanging wall is the southwest side of the fault. So this all here is the hanging wall, and this here is the foot wall. Okay, so you can count the fringes and count how many you have on both sides. And maybe, oh, I don't know if it's going to be easy to poll people if we don't have access to the chat. I don't know what my fellow instructors would like you to do here. You can, the Q&A obviously is not really the place for this, but maybe one person can issue a question, and then everyone can reply to that question with however many fringes they think there are on the hanging wall and foot wall. How does that sound? Am I talking to myself? Anyone out there?
I can hear you. So you mean are you going to break people out in breakout groups?
No. The Q&A, right? Someone can say how many fringes in the foot wall, or how many fringes on the hanging wall, and then everyone can reply and make it one comment, right? That's the thing. We don't want to be flooded with new responses, but you can all reply to the one question, and then maybe I can dig out the Q&A. Where's it gone?
Yep. So somebody pasted the question.
I thought it's a little hard to do the Q&A with many replies, but I think there's a live Q&A available right now. People can,
right.
yeah.
So we can, I'm going to dismiss one of these. Maybe we'll just keep Mohammed's question for now. And I'm going to type what I think the answer is. But well, I'm going to take an answer which is defensible. It's not the only possible answer, because there is a bit of interpretation involved. So now I've answered it, everyone else can try and answer it too. And I'm asking you basically to count how many how many fringes you see in here, and then you're gonna have to do a little bit of sort of working around. You can see there's patches of decorrelation here, so you can't just count straight along the fringe, along the profile line. You're gonna have to go, oh, in a bit, then navigate your way through this block of fringes. And yes, some people have noticed that the zero is actually half a fringe from the first fringe, so that's also a thing. 1, 2, 3, 4, 5, 6. And you maybe can take the PDF and blow it up large and stare at it a bit more to get a really good sense of what.
Range of answers in Q&A.
And some people haven't yet figured out the reply to question thing. It's okay. We won't punish you for that yet.
It's not that kind of class.
No. Okay. Well, my actual best estimate of what that is 21.5 fringes, but on a different day, it is quite possible to count a different number, just because it's really hard to count them when the fringes get really close together. And the fact that you could get slightly different answers is a manifestation of problems with unwrapping, because this is what we are really doing, is trying to take this repeated fringe signal and turn it into a continuous one. And also, of course, you can't always unwrap everything. You can see that you can't count the fringes through the decorrelated areas. So that's also a thing that you have to deal with when you're doing these. Okay, but then assuming that what we have is 21.5 fringes, can someone issue a new question, which is the next question in the notebook, which is, what is that displacement? How much displacement does 21.5 fringes or whatever the number that you came up with of fringes represent in millimeters or centimeters? Let's say centimeters. So Christy, thank you. You're not on. You have to reply as a question to this. What is 20 times 2.8? That's 56 centimeters. Okay, I'm going to type that. And once I've done that, people can go to that question and reply with their answers. And
I see some coming in.
yeah.
Still working it out. I like that.
Yeah. Not everybody has a calculator on their desk anymore, but I do.
Yep.
Okay. Yeah, people are getting it. Okay, and only 3 people have decided to answer outside of the question. I'm going to dismiss all your answers. You could reply here in the answered question part. That would
If
be great.
Once people submit it, if you scroll through the answers, you see there's a general trend, but there's also variability, which shows you right away how non-trivial this problem actually is, the problem of phase unwrapping. And try to get a computer to get this right every time is not that easy.
And we all know computers are dumb.
Well, mine certainly is. Can't be me. It has to be the computer.
Thanks for that, Christy. Okay, then the final question of this is, what's the direction of displacement? Is it up or down? Is someone going to ask that question? Someone going to ask me that question? Direction of displacement. Type answer. I don't know. I do know, but I'm not going to tell you. Let's have some brave people responding to this, which they think it is. Up or down? Remember, go to the answered questions and answer there. Some up, some down, mostly down, some both. Interesting. It went up and down. Down, 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 down. Okay, so the help here, whoops, excuse me, is remember the what it says in the caption and what it says in the text. Each cycle of colors from blue to yellow to red indicates an increase in distance between the satellite and the ground. Okay, so blue to yellow to red. As you go from the outside to the inside, that means the range is increasing. The ground is moving further away from the satellite, which, if you assume that all of the motion is vertical, means that the ground is moving further and further away from the satellite as you get closer and closer to the fault. So this means all the ground is moving down. So all the people that said that, especially the people who said it in a response to this question rather than chiming in here, got this right.
And, for this case, because for this particular one, most of the motion is up, down. This is also the right answer. Sometimes you don't know quite what the physics are, and basically what SAR initially tells you in SAR is that the pixels have moved further away, which could be either down or horizontal. So in this case, because Gareth told you, predominantly this is up and down, but it's not necessarily guaranteed, and you may not know that right away. So also remember that what SAR gives you is just a change of distance at first, unless you know more.
Yeah, I'm not even sure I told you what the viewing geometry was. I think it's a descending interferogram, but which means that the way would be to the west. Yeah, a way would be to the west, but anyway. Does that mean the hanging wall became the footwall as the northeast change was less? Well, remember, you can look at this line here is where the fault broke the surface, right? So you could treat this as like where the fault actually is, which means that the footwall side is over here, the other side of the fault. And I'll leave it to you in your own time to answer these questions here, although the unwrapping exercise that we're about to do will hopefully focus your mind a little on this, like how many fringes there are on the footwall side, and what the displacement is and what that direction of displacement is for those points. But what we want to do next is to try and actually make a profile along the interferogram that is unwrapped, so that you have essentially traced out what the displacement is at all points along this profile line. And as I said, if you can print out the PDFs, then you can take your profile grid and fold the paper along this edge and put it against this line, and you can actually trace it out on paper. But I know that most people don't have printers these days, and they're a nightmare to deal with anyway. So what I have provided you instead is with a Google Draw document. So hopefully if you click through to this, you will get something that looks like this, where I have basically done rotated the figure such that the grid lines up with it nicely. What you should do before you do anything is to click on make a copy, and you could call it you could name it by yourself or something, but my Dino profile. No, I can't spell Dino apparently. There you go. Because I am not going to give you permission to edit the original document. That belongs to me, and you can't have it. But now what you can do, okay, this is all lined up. I provided you with some dots. You can copy and paste these if you want more dots. And you can move these around. You can plonk them on the profile. But what you can do is take this vertical line and you can put it where you think the next fringe is crossing the profile line. And then using that as a guide, you can put your dot on the map in the right place with the right amount of displacement for, in the first case, what would be half a fringe of displacement, which would be 1.4 centimeters. Okay, and you can do that until you have traced out all the way from x to x prime, all of the displacements on this profile. Sounds easy? Or maybe it sounds difficult. I don't know. It's fiddly, but I don't think it's hard to do. It's just a matter of like trying to map things onto here, but I've given you a few hints. Whoops, I realize I can't do that. Okay, I can just highlight with my mouse, perhaps. The first hint is that, okay, at 2.8 centimeters per fringe, you can do some simplifying math if you like. 2.5 fringes is equal to 7 centimeters, and 5 fringes is equal to 14 centimeters. 10 fringes would obviously be 28 centimeters. Yeah. So that's one thing that makes some of it a bit easier. I think that you should, unless you're feeling particularly heroic, past a certain point on your profile, when the fringes start to get really close together, you can start going up in 5s. And one advantage of that is that 5 fringes is a nice round number of centimeters. And the third thing is the fault broke at the surface. All right, so you could treat that perhaps as a discontinuity in your interferogram. Instead of trying to count across it, I would recommend starting at either end of the profile and stopping when you get to the fault. And that will be easier to do than trying to figure out what the phase connection is across the fault. Does everybody follow those instructions and those hints and have a good idea of what you're trying to do? Thumbs up, thumbs down. Like the 4 people's things I can see. I see a few thumbs up. I assume people who are not sharing their screen have a much better sense of that. Yes?
I think everybody seems to be good with the instructions.
Okay. At this point, I will allow you to have a go. Patrick says, for the decorrelated area near the fault on the hanging wall side, would we need to assume the field measurement of offset like 15 centimeters at ends of the fault? Can the interferogram help us determine that large of an offset in a large area? If we look at the interferogram right here, you could argue that there is a decorrelation right between the fault and the largest displacements, which are somewhere around here, I think, because I think these fringes actually start to curve back in on themselves. So I would be very wary of trying to make any connection to the fault. That's why I say you're probably better off just starting over here, assume this is 0 and count in this way. Yeah. And obviously the other thing you're going to have to do, looking at this, if you want to deal with this decorrelated area, is you're going to have to use your eye to try and guess or interpolate where you think that fringe would be in here. Can I repeat unwrapping the interferogram along a profile, please? I mean, that's the purpose of this whole exercise, is to try and estimate on this grid where each displacement is on this profile line. That is unwrapping the profile, unwrapping an interferogram along a profile.
I think he would want you to redo it. But
I'm not doing it. That's the point. I will do it at the end.
so I guess the answer is no then.
Yeah. And as I say, you have to make your own copy of this thing, because otherwise you'd all be trying to edit the same document, and that's not right. You need to do it on your own. Typically we give people 10 minutes to have a go at this, right? We are running a little late, so I'll give you until 2:10 Pacific time, 10 minutes after the hour. And if anyone else has questions, I guess this and especially people who are really efficient at making profiles, then this would be a good time to start asking questions. The homework for this exercise is to actually complete the profile yourself and to answer all the questions. There's also questions in the notebook at the very end, after you've done the profile, where you have to do some trigonometry and stuff. I don't know if we need some more of that incidental music. Not really.
I could put the timer up if you want me to.
What do you think, Franz?
Well, absolutely. The music is fantastic.
Yeah, put 8 minutes on the timer.
Do you want anybody to share once they're done?
Yes.
Oh, can people? I don't know.
We usually do that.
That'd be cool. No pressure.
No. Like the Jeopardy music would be good, like for the.
Dum, 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 dum.
Yeah.
We should put up the L-band interferogram with that Kamchatka earthquake next time. Or there's going to be lots of really cool ISCE interferograms next year.
Yeah, I've been processing the Kamchatka ones. There was a really annoying ionosphere error in the first ALOS 2 interferogram, which I have yet to conquer. maybe when Eric is on, compare notes.
Yeah, I think Eric had some, he shared some stuff, but he had some issues also with the atmospheric correction in ice.
Yeah.
For that one.
Yep. I couldn't get it to sample, to take fewer looks. There's some annoying thing where I wanted to estimate it on a much finer grid than normal, and it wouldn't let me. And actually, the corrected interferogram looked worse than the original.
Yeah, I think it's the same experience.
Yeah, I actually got a coherent Sentinel-1 interferogram of it. So, hey.
Really? Over like what, 12 days?
Yeah, I was really surprised.
I guess it's summer. And there was an eruption following it.
Oh, really?
Yeah. There was some, I wouldn't say dormant, but quiescent volcano erupted then just a few days later. And
like shaking shaking a can of Coke, right? Yeah. Liberate all those bubbles of gas. I don't know. I'm sure those volcanoes got a good shaking.
I do not think we have a timer.
Oh no, there is one. I see it in the
Do you see it?
At the
corner.
Yeah.
Right-hand corner next to the recording.
Yeah. Right at the top of my screen, right on my UR screen sharing button, there is it's got 4.5 minutes left. Meanwhile, I'm SSHing into my computer with the interferograms on it. So Christy reports trouble getting it to copy.
Is that the right theme music.
So click on Google Draw. Click. Does make a copy show up for you, Christy? Oh, I should have said. No, grayed out. Interesting. Does anyone else have that problem? I wonder if it's whether or not you have a Google account. Yeah, under the file menu. If you have access to a printer, then you could try doing something where you print out the grid and hold it up against your screen, scaled appropriately, or as you could try printing out if you have a color printer, you can print out the color PDF of the grid and do it that way. Yeah, I don't know about screenshots. That might be something that requires a little sort of office hours help.
The first is tonight.
It is.
One minute left for everybody drawing.
There's always tomorrow. There's always the morning office hours, or the California morning office hours. Okay.
Okay, do we have any brave people that want to share their screen?
Yeah, I can stop. Any brave volunteers? You can raise your hand maybe if you feel sufficiently confident in your. And we can also wait in an awkward silence until someone does.
And while there are wrong answers, this is a judgment-free zone.
Right, we're here to guide and train, not assess. One hand up. Don.
It's Anne. That's not fair. Oh, it's Donnie.
Donnie, would you like to share your screen and unmute yourself? So there's a green button, hopefully, that says share, and you can click on it. Yeah, there we go. Okay. So do you want to talk us through your interpretation? You should be able to gesture at things with your mouse pointer as well.
Wait a minute. So point to my screen. Let me undo this. Wait.
Oh, we could hear you. We can hear you, and we could see it.
All right. See my mouse?
Yep.
Yeah. All right. So, well, it seems to me like we got like one fringe over here. Like it's like directing like indicating a downside. So each fringe is a downside of 2.8 centimeter, and as we go along the profile through the fault line here, it's subsiding even like deeper.
Uh-huh.
And at the fault line, this fringe here is also indicating an increase in range distance between the ground and radar. So we're not at the surface here, but this side is also being like pulled down somehow, and then it's coming out, like coming up again somewhere, it's fading towards the X prime.
So what's the basis of your estimate at the end of that jump? Like how did you come up with that displacement there?
Yeah.
Yeah.
You mean like this side?
Yeah. Yeah. So one piece of advice I give people is like start at 0 on both ends, right?
Right.
So assume then that you have 0 displacement at X prime. And if you trace inwards towards the fault, what's the sense of the movement?
It's going down. Because
Well, okay. What's the sense of color? It goes blue, yellow, red, or red, yellow, blue?
This is red,
Yeah.
yellow, blue. All right, then it's the opposite.
Yeah. So on one side of the fault, the fringes go blue, yellow, red. On the other side, they go
Right.
blue, red, yellow, blue, and then in between there is a fault and maybe a decorrelation. You can't really tell. So I would be very hesitant to connect the two sides of the fault to each other, and they do seem to be moving in different directions.
Right.
Right? How's that sound, everybody? Does that help?
Like how do you determine, like it could be like blue, yellow, and red as well? Like
well, if you started at the fault and the fault had moved up, and then going from the fault towards X prime, it's going down, right?
Right.
But the key thing is that probably it's going down from a higher position.
Right. Okay. Right.
But thanks for that. That was hopefully instructive for people.
Okay. Thank you.
You could stop sharing, and I will share my screen just now. Let me get this to. All right. I didn't want this. I didn't want these. I wanted this. Okay. So my attempt to do this. Okay. So we start at 0 fringe. The first fringe here is, remember, half a fringe, right? So the 0 level to here is 0.5 of a fringe, or 1.4 centimeters. And we have, as we have discussed, this is the hanging wall side. So things go down. This one, I eyeballed it to be about here, although there is definitely some slop where this could be. Somewhere in here, you can see the curvature of the fringe and so on. And this is 1.5 fringes, which I think is 4.2 centimeters. This is the third, the second full fringe. So 2.5 fringes here. That's 7 centimeters of movement. And then I started going in 5s because it gets difficult to count every single one of them. And that's my hanging wall side. And as I said, I thought I got to 21.5 fringes doing this, approximately. On the immediately next along the profile, there's an area of decorrelation, and where you have decorrelation like this, you really can't unwrap across it. It's unless you can connect to it from some other place, which around here you can't. You just stop, and instead you start again over here at 0. And I think this is half a fringe to here, and that's where you have a transition from blue to red. So I'm going to say that's 1.4 centimeters of now movement in the other direction, because the fringes go, as we just discussed, red, yellow, blue, which means they're moving towards the satellite. This is another red, yellow, blue. That's 4.2 centimeters of uplift. And then right here, you know, you're at the very heart of blue. So going to say that this is basically 2.5 fringes of deformation by the time you get to here. So overall, I have this pattern of asymmetric, steep subsidence on the hanging wall side and gentle uplift on the footwall side. And that would be my interpretation of this interferogram. How's that sounding? Some people thumbs up. So your job for homework is to complete a similar interpretation yourself, like actually go through and draw the profile line out. And answer the rest of the questions in the chat. I can show you a few more things actually, because I do this slides. Another thing that I include in the folder, I think I will double check. I think there are KMZ files in there. You can actually plot them in Google Earth. So if you're curious what this actually looks like on the ground, this is a view of the Dinar area in Google Earth. And this is the interferogram overlaid on top of it. So what can you see? You can see in the area of the footwall side, there is actually a range of hills and a fairly steep slope. And the fairly steep slope maps to where the fault projects to the surface. And then on this side, there's mostly flat land. And there are even some lakes, sort of small lakes that are formed up against the hillside here. And you can notice also that the lakes are where the signal decorrelates. But perhaps also those lakes are in the area you would expect them. They're actually the lowest points on the ground from each earthquake. That's an area that's area that's subsiding probably during the earthquakes. And the mountains, such as they are, the hills, are areas where the ground was uplifting in the earthquakes. So there is a relationship between the topography and the deformation there. So hopefully that's helpful. You can sometimes, yeah, obviously, like we gave you an interferogram with no context to do this interpretation. We did give you some information, but sometimes you can derive clues like this from what you see in the landscape to try and help your interpretation of what's going on in the interferograms. Can we also see there are areas of vegetation, and I think some of them don't do so well in the interferogram. It's usually because agriculture is not good for InSAR. That you're basically changing the land surface, you're changing the scatterers in each pixel. There are areas where you'll get temporal decorrelation just from changes to the ground from one growing season to the next, or from between when you have crops there or no crops. You will get decorrelation, and some of the other features relate to other hydrologic features, like there are streams, those also will decorrelate, and other things. Right. So that's the exercise in as I say, your homework is to finish this, to make PDFs of or screen grabs of your finished notebook and profile, and upload them to Moodle. There is a place for this homework on the Moodle site. Where is my window?
There is a question by Alexandra about how typical this kind of amount of deformation is. This is typical for there to be dramatic hanging wall subsidence versus dramatic footwall uplift.
Yes. Dip slip faults in general are quite asymmetric in their deformation. That's a kind of a trend. The ratio is somewhere usually between 1 to 5 and 1 to 10 relation of like motion in either direction. For normal faults, yeah, one part uplift to 5 to 10 parts of subsidence. And for reverse faults, which move in the opposite direction, the reverse is true. You get lots more uplift and not much subsidence. Yeah, that is pretty typical.
And Camilo, it's a little bit experience, where do you, try to interpret in the noise, and where do you not do that? Gareth's a little bit further away from the fault zone, did do some interpretation of what the fringe patterns might look like. It's probably a bit safer to do that at distance, while near the fault, where the gradient is fairly high and where lots of other things can happen. I'd rather basically not try to interpret in the noise and leave that as a gap where you just don't know what's going on.
Yeah, we have models obviously of what that fit this deformation pattern. What you see in those is that the subsidence starts to reduce as you get back towards the fault. You can see that the maximum displacement is away from the fault. That actually implies that the maximum movement on the fault was not at the surface, but it was at depth somewhere. So the fault was somewhat buried, and you only get, like, I think 30 centimeters maximum surface offset on the fault, whereas we saw 60 centimeters of subsidence away from the fault. That kind of implies that more movement happened at depth than happened at the surface. And so in the model, you actually see the deformation go back up again. Right? So there's a subsidence and then a small amount of not uplift, but reduced subsidence. The subsidence peak maxes out at some distance from the fault and then starts to decrease. But yes, I still wouldn't try and interpret the profile across the fault. It's good practice to start at either end and work your way inwards and see how far you get.
There's a question I just answered about the homework due date. So in the end, in the grand scheme of things, the homework needs to be in by the end of the week or early next week. But because there's homework every day, it makes sense to try to complete the homework as soon as you can, so that you don't fall behind as much, and you can work on this particular day's content.
Is that because the far field deformation is mainly subsiding? Well, no. The far field deformation should be 0, and then it's asymmetric. Like, you have some uplift and lots of subsidence, and that's purely from elastic rebound processes. And the other thing, some of the questions, I mean, there are versions of this exercise where we run these in geology classes, or I do at my university, and we ask a lot more about how representative is the earthquake deformation of the long term, and it isn't fully representative of the long term, because you have a long period of time where the crust is bending and the fault is being loaded, and then this is kind of the unloading phase of the fault, and so you can't really ignore the hundreds of years of deformation that goes before this, which are somewhat reversed from what happens in the earthquake. Like, the far field moves a lot more between earthquakes, and the near field moves most in the earthquake itself. And in the end, you would expect actually the pattern, the long-term pattern, should be like a sawtooth, like square wave or something, but it doesn't quite look like that in the landscape because there's erosion and other processes going on. Geology is a bit more complicated than modeling interferograms. Anyway,
in the interest of time, we probably should
stop
that conversation and maybe point out real quick on the syllabus that we do have a office hour coming up in a few hours at 5 p.m. Pacific time. So that's like 3 hours from now.
2.5.
where you can ask questions. And then we have another office hour coming up tomorrow morning at 7 o'clock Pacific. So whatever fits your time zone the best, come and attend those and bring your questions. They are really there to help you keep up with the course, make sure that you can complete all the homeworks, etc.
And also note that the first hour for tomorrow is also set
Yes.
aside for recapping and review of things that happened today and questions that arose that you didn't get to have answered at a different time.
Yeah, and so the office hours are optional. The main session is mandatory, and you also need to attend it because we have a lot of ground that we are covering. So if you can and if you have questions, show up at tonight's or tomorrow morning's office hour. Otherwise, we'll see you tomorrow.
Do you want to show just really briefly clicking through to Moodle and showing where the homeworks should be uploaded and stuff and answered?
Bring Moodle up real quick. Is that linked from here?
Yeah, in the links.
Here we go. This website management system. Can you see that?
I can.
Okay, so this is the Moodle page. And so we are in day one. To get to the homeworks, you can either click to the day one section, and it gives you sort of an outline of the things we talked about today. And it includes also the homework assignments. So there's a homework 1. If you click on that, you'll get to the homework 1 exercise. For homework 1, it's basically answering some questions directly on the platform. The other homework is homework 2 here, where you then will have to upload and submit a document. So when you go through these sections, you can then, I guess, go in. I'm not in student mode. It's probably a way of doing that, but I don't quite know how to.
You click on FM.
Yeah.
Yeah, and then switch role to.
Excellent. So here you can then add your submission, and in this case,
I feel like you can upload multiple files if you want to.
Yep, there's a way of uploading a file here.
You just do it twice through the same interface. So if you have the notebook printed out as a PDF, do you want to show that too?
What,
saving,
like how?
Saving the notebook output.
Oh, I see. Let's see if what are you seeing now?
I am not seeing your screen. You might have to share a different window. Or
yeah, hang on. Say we had this particular notebook today. The best results I tend to get is when I go to File, and then there's an export menu. Oh, save and export notebook as, and then I export it as HTML. Oh, well,
you broke it.
I'm not sure what the PDF does.
You can also print it, right?
Oops. Oh, here's the PDF. So there's a way of exporting it as a PDF. That is okay. It doesn't always give you the most beautiful result, but this looks okay.
Yeah,
so
we can't see it. We're taking your word for it that we can't see the PDF.
Oh, I'm sorry. Silly France. Okay, I'll try this one more time. I'm just going to share my screen. And so this is the PDF I got.
Oh, yeah.
So it looks pretty decent with all the outputs in it. Then let's see if there is a print option.
There is.
The print option apparently that doesn't work either. So I would do the export as PDF. I'm going to get with the OpenScienceLab team and see why the HTML output does not work. But if you go to save and export and then as PDF, you get a decent rendering of your notebook. And in the meantime, I'm going to figure out the issue with the HTML export and get that fixed.
Super. So thanks, everyone.
Glad you asked me, because this way I can get that fixed.
Yeah. Thanks, everyone. It's been a great day.
Yep. See you guys later or tomorrow.
See you office hours or tomorrow.